We have about 10 minutes before we start. Can I just check that my audio is working okay and someone can say in the chat if they can hear me? Thank you, Ray. That's good. Back in a few minutes.
Testing, testing. This is a microphone test. I don't know if anyone can hear me or can see me as I call out to the void.
I can hear you.
Yeah, me too.
And see you.
And see you.
Great. Thanks, everyone.
Okay, we'll be starting in about 1 minute from now, 45 seconds from now. Thank you, David. Good timing. Nice to see you.
Hello, likewise. I believe I have a circle in the as my on my so-called avatar. I believe it needs to be a square. I don't know if someone can give me speaker privileges.
I think Sarah will do that any second now. Sarah, so we we're ready now to start. I'm waiting in case anyone gets picky because they joined on the last second.
David, when I've loaded your slides up, I'll give you presenter abilities, and then you should be all set to go.
Great, thank you.
Okay, welcome everyone to the GNU Tools Track at Linux Plumbers Conference, the second year running. Thank you very much to LPC for making this possible. For the second year, we haven't been able to hold GNU Cauldron due to COVID-19. We hope to get that back on track next year, but this has been a very great ability to interact with the wider Linux community. I'm Jeremy Bennett. I've chaired the organising committee this year, but thank you very much to my colleagues on the organising committee and the programme committee. And thank you in particular to Sarah Cook, who actually has done all the heavy lifting, and my job is just to be at the front here and welcome you all. Sarah will be attending all the meetings. She will do her best to respond to questions promptly for you, speakers have her email address, so can email her with any concerns. So without further ado, our first speaker today is David Malcolm, and his slides will appear shortly, and then I'll hand over to David. David, all yours.
Thank you. I'm just waiting for the slides to appear. Hello, my name is David Malcolm. I work at Red Hat on GCC, and this first session is going to be about what's new in GCC in the -F analyzer option. I assume everyone can hear me and can see the slides. And so, where are we? Next slide. So I'm going to be talking about what is the -F analyzer option, how it works internally, what the changes I've made so far for GCC 12, and the changes I'm hoping to still make for GCC 12 before feature freeze, which is probably early November this year. So what is -F analyzer? It's a static analysis option. The command line option enables a new interprocedural pass, which I added in GCC 10, and it does a much more expensive analysis of the user's code than we've traditionally done for warnings in GCC. Internally, it tries to attempts to walk all the paths through the user's source code and builds what's called an exploded graph, which is a directed graph that combines both control flow information and program state. So each node in this directed graph has both a program point, which is a combination of the control flow location in the control flow graph, but also interprocedural information, a call stack. And it also has a state. The program state's a bit more involved. It has the first bullet point is what we call it the store, which is a abstract representation of the contents of memory. It's a mapping between symbolic descriptions of memory regions and symbolic values that those memory regions can hold. So, for example, it might represent that a particular global variable has a particular constant value. We also store constraints on those symbolic values. So, for example, we might know that at this point on the execution path, the initial value of parameter I of a function is less than the initial value of parameter n of the function. As well as the tracking memory contents and constraints, we have some state machines. So, for example, that the tracking heap APIs, we might know that a particular pointer has had free called on it. Another state machine example is a taint state machine. This one's much less, this one's more of a proof of concept still at this stage, where we track that a particular value has come from an untrustworthy source and hasn't yet been sanitized, so that we can complain, for example, if it gets used as an array index. And those state machines both track states per value, but and I'm seeing people talk on IRC, but other state machines can be just global. So we have a state machine that's just one big flag saying, "Oh, we're within a signal handler at this point in execution." And the analyzer attempts to explore all interesting paths through the user's code. I have various heuristics for doing so, but because we're just tracking an approximation of state, and because we want to ensure that the analysis terminates in a reasonable time, and indeed terminates, there are various ways in which we can have false positives, where we complain about things we shouldn't do, and false negatives, where we fail to complain about things that we should have done. So the analysis is neither complete nor sound, to use the jargon. As we explore the user's code and build this exploded graph, we store diagnostics into it. And the reason we don't emit them immediately is because once we've explored the code, we can do deduplication, and we can try and find some nodes are really effectively the same diagnostic. Sorry, some diagnostics are effectively the same diagnostic as another, and we try and find the simplest one that we can emit to the user. And as we find the simplest path through the graph, we try and find the simplest feasible path through the graph, so that if we check a flag is like if foo, we also want to make sure that foo is still true on later edges in that path, so we don't, that's another way of rejecting certain false positives. And finally, having done that, we express the simplest version of each diagnostic to the user using ASCII art to express the path through the code. So in the initial implementation of this in GCC 10, I added 15 new warnings. The first few, the motivating case was the double free detection, and there are a few others relating to it using the heat state machine, use after free as a leak detection, and various others. Similarly for the file API. One of the nice things about the exploded graph representation is it makes it relatively easy to implement set jump and long jump support. So there's a couple of warnings about that. There's the signal handler one, where we can check interprocedurally, are we in a signal handler, and complain if someone calls a function that's known to be unsafe to call from a signal handler. There's the taint thing, which is unfortunately still a proof of concept at this stage. And a final one is an attempt to detect if passwords get written out to a log file. Again, still a proof of concept at this stage. For GCC 11, one thing we did was we generalized the GCC's existing malloc attribute, which used to merely be a way to hint to the optimizer that this pointer doesn't have aliases, it's a freshly allocated heap pointer. But we added an optional second parameter, which is what's the free function for this allocator. And once you have that, well, the analyzer can complain if it sees a mismatching deallocator. And it also just marks to the analyzer, this is an allocator deallocator pair, and it means it can do double free, leak, and all those other detections on a custom allocator. And I also added a couple of warnings about undefined shifts, undefined behaviors and shifts, and undefined behaviors due to attempting to write to something that's read-only. Also for GCC 11, I added some initial plugin support, the ability for a plugin to register its own state machine. And the example that's in the test suite, CPython, the Python API, has allows you to embed a Python interpreter inside an application, or to wrap libraries with Python as Python extension modules. And the API has one big global mutex, the global interpreter lock, where all access to that API and all access to Python objects have to be guarded with this mutex. So I wrote a simple plugin in which, and here's an example where some code has done pybegin allow threads to release that lock. Maybe it wants to do some wait on some I/O or do some expensive computation, and then it tries to manipulate a reference count, and the analyzer correctly complains that, yeah, you can't do that, you need the lock in order to do that. So back in the spring, I was looking at what should I focus on for GCC 12, and I had initially thought I would look at C++ support, but I felt that what I really wanted to do was try and improve the analyzer support for C, and I looked at a few different areas, and I'll talk in the next few slides about what I looked at. So I had implemented new and delete support for C++ in GCC 11, but I hadn't implemented exception handling support. And I looked briefly at it, and it's quite it's quite involved, and I was thinking, well, maybe I'll get back to that. In the meantime, I mentored this summer a Summer of Code student, Anka Saini. Forgive me if I'm mispronouncing your name, and he did a lot of work generalizing how the analyzer handles jumps through function pointers, and use that to implement support for virtual functions for C++. But what we still don't have is support for exception handling or for runtime type identification. That's C++'s dynamic casts. And so, and that's, well, it'd be an interesting, if someone wants to volunteer, it's a well-defined area that they could step into and work on for the analyzer. But I decided what I really wanted to focus on was improve. There's still a lot of C areas that we could support better. And so I thought let's focus on doing that well, rather than attempting to branch out into C++. And next slide. Yeah, so I thought there would be a couple of areas I could look at for better C support. One would be buffer overflow detection. That's a really important issue for C. The other would be detecting uses of uninitialized values. We already have that in GCC, but this, because it's using the analyzer's infrastructure, would be a path-sensitive analysis of and in procedural analysis of uninitialized values. So I did some prototyping back in the spring of trying to implement buffer overflow detection in the analyzer. Now, some of that work, or some of the sort of the enabling work for that, is in trunk right now. So, for example, a few slides ago, I showed the sort of state that I'm capturing in each node in the analysis, and that state I now capture the sizes of dynamic allocations. So, and these are captured symbolically. So, if you have some code that says P equals malloc size of, or sort of n times size of something plus size of something else, then that will actually get captured as a symbolic expression in the program state. And the other thing I added was a consistent place in the analyzer for tracking. Here's all memory accesses, all reads and writes that the program does. Here's a place to put checks there, so that we can add diagnostics. So the logical thing to do would be then to try and add a buffer overflow detection check at that sort of checkpoint, using the size information that I put in. So I tried doing that, and I tried categorizing all memory accesses sort of into three categories, which is one is like, we know this is a valid access, all is good, or we know that this is definitely invalid, or at least partially invalid, and that we should complain about, but also we don't know. The analyzer just doesn't have enough information at this point. And I took it as far as creating the sort of Boolean symbolic expression that describes this memory access is known to be fully valid, and then evaluate it. And it's a tri-state. We have it's known to be true, it's known to be false, so we know there's at least some part of the bounds that we've gone beyond, and by far the most common case, the unknown. And so my prototype was emitting like hundreds of possible out of bounds rate to array index I when I is greater than or equal to n, or I is less than 0, and I'd be looking at them going, well, yeah, that's how array accesses in C work. This is not useful information. And I thought, well, it's just a wall of noise. It's not particularly useful to a user. I thought, well, how can I make it useful? And I had the idea, well, actually, there's a fourth category, which is, can an attacker influence one of the sub-expressions within this? Is this memory access valid condition? And if so, well, that's really important information to the programmer. So it kind of got me thinking about, well, I have this prototype of taint detection. Let's pursue that. And it got me thinking, well, what are the values? Can we decide for arbitrary C code, what are the values that are trusted and are known to be okay? What are the values that are untrusted that need sanitization that we should take great care about? What's the attack surface of the code? What are those trust boundaries? Can we decide that for arbitrary C code? I think the answer is no, but there are important projects that and ways that we could annotate those projects that for which we could basically identify that trust boundary. And I thought, well, the Linux kernel is very important to Red Hat. It's important to a lot of the attendees at this Linux Plumbers conference. And so having a way of annotating that boundary between user space and kernel space seems like really a fruitful thing to explore. We have in Linux has a copy from user, copy to user to express going across that user space kernel space boundary, and there are system calls which are where the parameters and the arguments coming in through system calls could be hostile, and similarly ioctls, data coming from the network and so forth, or from USB devices. And so I did some experimentation with, can we mark up the kernel source code in a reasonably lightweight way to try and identify that boundary between user space and kernel space. So, for example, GCC already has one of its attributes. It has an attribute access, which can be read-only, write-only, read-write, I think. And it basically lets you express what direction data is flowing in on a particular, for a particular pointer in a parameter to a function. So I tried introducing, well, an untrusted read and untrusted write. So, for example, for copy to user, you have data that's inside the kernel being copied back to user space. And if you have, say, an uninitialized stuff on the stack that's being copied back to user space, or maybe whatever was in there, it could be sensitive information that's getting leaked back to some process in user space that might be running as a different user to whatever call the system call before. And so we can annotate with an untrusted write that's going, that we could have a information leak there. Similarly, for copy from user, we could maybe have an attribute to mark that up as an untrusted read, so that the analyzer can know that values coming across that boundary, this is a trust boundary, and values coming across it need special care. One nice thing about the kernel headers is that there's a single macro, well, there's a lot of macros, but there's a single place where we can add I tried an attribute tainted, which I invented, and it basically says, well, any arguments to this function, don't trust them. And by putting them in this particular macro, suddenly all of the system call implementations across the whole kernel get marked with this attribute, and which is really nice, because it seems that users hate having to add attributes to their declarations, and if you have to do it in dozens and dozens of places, that's kind of going to be a non-starter. Whereas if it's like just one single place and you've got like a hopefully 5-6 line patch to the kernel, that's a much easier ask. Sorry, that's a management jargon. That's much easier to patch to get in, I hope. Similarly, there are a lot of places in the kernel which we have callbacks where functions are registered in tables of callbacks, and I was able to add an attribute to the field declaration. So here's one for config.fs where data is being stored, but there's a similar one for ioctls where we can mark that field with an attribute, and then the analyzer can see any function that gets used as sort of registered as a callback for that field. We can then mark that function as being we know that it's getting stuff from, say, it's an ioctl handler or it's handling network data. We know those values need extra care. And again, it's just like one place, or then all of the ioctl handlers in the kernel get marked with that attribute. So I started looking at old Linux kernel vulnerabilities, and I found there were two general categories of vulnerability that looked quite fruitful to try and detect in the analyzer. One is information leaks, where, as I said, if you have uninitialized data gets copied back from the kernel into user space, and that might leak information, for example, just what the layout of the kernel memory is, which gets randomized. But if the attacker knows where certain things are stored, that gives them information to make another attack more useful. It's relatively easy to detect, or at least I thought it was going to be, so I thought I'd look at this first. I'm something of a kernel newbie, so I thought I would get my feet wet with this. Historically, it's been regarded by some as rather low severity, and which is debatable. And also, a marvelous thing in GCC 12, they have a mitigation for it. We have a new -f trivial auto var init option, which will mitigate a lot of these problems. But of course, the same source code could be being compiled by other people with an older compiler. So it's good to get the source code itself fixed. So it's good to detect these. And the other issue I was looking at is taint, where if data is coming from the user space or the network, or even a hostile USB device, and that data is being used for, say, an array index, or the size of an allocation, or even as a divisor. So the attacker can inject the divide by 0. And this seems harder to detect. I have a prototype of it as of GCC 10, but it's turned off by default because of scalability issues. And it seems relatively higher importance because you can crash the kernel, or you can get root using these kinds of attacks. So looking at those, here's an info leak from 4 years ago. It's a AAC SRB reply struct with a bunch of fields in it. And the code, hopefully this is visible, is we make one of these on the stack. We initialize all the fields, in fact, and then we have a copy to user to copy all the values back to the user so they can get the data. Now, and the analyzer successfully reports correctly that there's a information leak here with a rather verbose potential exposure of sensitive information by copying uninitialized data from stack across trust boundary, exposure through uninit copy. And it shows the source region of the copy is created on the stack here. So it identifies whether it's on the stack or on the heap and how big it is. It's 52 bytes. And a copy happens here. And you might wonder, well, we initialized all the fields. What's the problem? And it says, well, 2 bytes are uninitialized. And it says, well, there's two bytes of padding after the final field that get uninitialized. And I've got the wording, the warning is worded so that it tries to identify all the different fields, padding areas, that are either uninitialized, fully uninitialized, or partially uninitialized. And I track it at the per bit level, by paths and interprocedurally. And it also would actually generate a fix-it hint suggesting to initialize the object on the stack, which can be, from which GCC can auto-generate a patch. And so I was looking and thinking, well, I want to have an analyzer use of uninitialized value warning that was in the old patch kit that I originally submitted for GCC 10 to drop it because it wasn't very well implemented. And so I decided, well, now's the right time to implement it. So I had to do a fairly large amount of hacking to the store. That's how we track the abstract description of what's in memory. I'd already had to do a big rewrite for GCC 11, so I had a somewhat large rewrite for GCC 12 as well, and also how bit fields are handled. But now at least we track at the per bit level what's been initialized or not, and which is of course important and allows us to do this more general warning as well for C code. I also found I had a big bug in how switch statements were handled, so that needed a fairly large amount of work as well. Another example here, there's a bug in this code where you have a field on the stack. So an object on the stack, we copy from user to it, we do some stuff with it, and we copy to user to a different pointer. And there's a bug in this code because if the copy from user fails and leaves this untouched, it's uninitialized, and then if the copy to user succeeds, you have an info leak of how many bytes that is. And in order to detect that, I found there was a problem in the analyzer where I all my state updates are done in place, and I did that because basically as an optimization, because we weren't using C++ 11 when I was first working on the analyzer, and unfortunately that's baked in rather too deeply now. So it means that every control flow edge, there's it seems there's a single output, a single possible outcome for it. And so I had to add in some special casing for the rare case where you want to split the analysis, or I use the jargon, bifurcate the analysis. So I can do a when the copy from user succeeds and copy from user fails, and basically split the analysis at each copy from user call. And that's in trunk now with special handling for realloc, where we want the 3 outcomes of growing the thing in place, having to remove the allocation, or just failing. So taint detection. Here's an example from 10 years ago where I've omitted a whole bunch of stuff of fields, but basically you have a slot integer and there's a pair of slots. This gets copied to the stack from user space. We grab a pointer to it. We do this bit of sanitization, and then we use this to look up an array index and an array elsewhere in the kernel. Sorry, we don't just look it up, we write to it. And this has a bug because, I don't know if anyone can see it, but well done if you do, because int is signed. And so although we validated that it's not beyond that 2, it could be negative, at which point this write is an arbitrary write to somewhere in memory, controlled by user space. And so the analyzer, my prototype of the analyzer successfully complains about this. Use of attacker controlled value info num in array lookup without checking for negative, and it shows the path to get to that. And so I've been working on a prototype of this, and I got lots of unit tests, lots of reduced kernel code, and I thought, well, what? But unfortunately, the Linux headers are really complicated. They've got lots of conditionals in them, and so I've got an integration test, what I like to call the world's worst kernel module, antipatterns.ko on my GitHub, and in which I try and make as many mistakes as possible, and I can verify that my patched analyzer does detect this with the Fedora kernel headers. Another issue I ran into when trying to scale this up onto the real kernel with real headers is the Linux uses a lot of inline assembler. So I had to add some primitive support to the analyzer for 5 minutes, thanks, for handling inline assembler. What I don't do is look at the actual opcodes themselves, because that would just be a huge scope creep. I have some heuristics which effectively suppress a lot of false positives. Now, and I scripted basically grabbing my patched analyzer code, building that, and then using that to build the kernel. And I've been running it on recent Fedora and RHEL and upstream kernels, and fixing the various false positives that I ran into, and reporting the one true positive that it finds in a all yes config upstream kernel, some code that we don't build in our distribution kernels, and that isn't yet fixed and is and not yet public, and therefore the reason why basically in terms of upstreaming this, all of the support code is in GCC trunk, but the kernel specific tests are still just in an internal Red Hat repo, because it finds vulnerabilities in the kernel, which is, or at least one, which I don't want to, hey, here's a tool for finding 0 days until the kernel community has a chance to fix them. So in trunk, we have the new use of uninitialized value, interprocedural and per bit and path aware version of uninitialized warnings, and a whole bunch of other cleanups and infrastructure needed by info leak and taint detection, but also helps all C code. And so the info leak detection, as I say, isn't yet itself in trunk, but it's basically done technically, sort of an implementation point of view, and is basically ready to go in, but I don't want it to go in because as I say, it would be a 0 day. But there's some sort of, we can have a bike shed painting discussion about what should the syntax for the attributes look like, and also where should this code live? Like, can I express all the semantics I need to about the kernel generally enough that it isn't kernel specific, or is this inherently kernel specific and therefore should it be a plugin or something? The taint detection is, I'm still working on the implementation. There's still bugs and misses stuff, and there's some state explosion. But I hope to have it done by the close of stage 1, and similar scope considerations apply as for info leak detection. So I've spoken about the analyzer, how it works internally, the various changes I've made to GCC 12 which benefit all C handling, especially the better uninitialized value detection, or this new uninitialized value detection, and the warnings that are very much kernel specific, relating to that user space, kernel space boundary. So thanks very much for listening. Thanks to LPC for hosting us. The project's homepage is on the GCC wiki at the link on this slide. Also, I'm co-running with Carlos O'Donnell a session on this at the Kernel Dependability and Assurance mini conference on Thursday. And I'm pretty much out of time, but if anyone has any questions, I guess, well, I mean, I guess you can ask them on Thursday and we can have a discussion about it there, because I think the next session is starting in a couple of minutes.
Thank you, David. Yes, you've got a couple of minutes of questions, and like I say, there's plenty of vehicles for asking questions throughout the meeting. So while any questions come through to David, and there were a couple of questions I see from Richard Biener in the chat. Christoph and Eric and Philip are up next. I guess, Eric, are you doing the presenting?
Yes, I will be doing the presenting.
Okay, so
I can't see the chat. It's been syncing for the last 40 minutes. Well, there's been a spinny thing in the chat. So, if you could repeat the question, please.
Are there publicly available test suites for static analyzers? They must be an active research topic after all.
There is a test suite. I think it originally came from, it was one of the car companies. I think it may have been Toyota. I think it's the NIST, or the SAMATE, SAMATE, and I can maybe post links for that. And yeah, so there is a public. It's like, here's a set of sort of benchmarks, as it were, for, do you detect this? Do you probably not emit a false positive on that? And I've played around with those, but I haven't yet managed to integrate it into my test suite.
Okay, thank you very much, David. Always good to hear from you.
Thanks for listening.
So our next talk is from Eric Okoa, Christoph Mulner, and Philip Tomish. And I think, Eric, you're doing the actual presenting, and I think you're just going to share your slides. Is that correct?
Yes, I will share my slides in a second. Just one moment. Oops.
I should have said to speakers who haven't seen the various emails, because there's been a lot of advice to speakers, you will get a little card flash up for you. You've got 5 minutes left and then 1 minute left. And when time runs out, I shall step in.
Okay. It's almost finished uploading, but I uploaded a PDF named points2.pdf, and I think, yeah, perfect. All right.
All yours. Thank you.
Thanks. All right. Hello, everyone. My name is Eric, and I'm here to present the work that me, Christoph, and Philip have been doing for the last year and a half. And it involves some technologies, some new technologies, and some work that we did in the past that we've already presented on the Patches mailing list. So let's start. First of all, I would like to start by introducing Souffle. And I'm going to be using some of the resources available on their website. And so I've included the link of the website below. But Souffle is, as GCC, it's a compiler, and it compiles data log language down to C++. And so what does this language look like? Souffle is a declarative logic language, and as such, instead of functions, it has relations. And in this simple program that we're going to be building, we are going to be receiving as an input edge list to describe a graph, and we're going to be making the output list of tuples for all nodes in the graph that can have a path between them. And so here we're just declaring the edge. The nodes are represented as numbers. So if there's an edge between nodes x and y, then there's going to be a tuple in this relation. There are two different kinds of relations that can be described in Souffle. One of them is the input relation, because we're going to be receiving this as an input, either as a comma-separated value list, value file, or also you can interface via C++ to send input to the Souffle program. Now we are declaring the path relation. Again, the path relation will contain a tuple if there's a path between nodes x and y. And we're going to be declaring it as an output path. But now we still need to build the rules that will actually specify what path means, right? And so here, one of the first rules is almost axiomatically, if there's an edge x and y, then there's a path between x and y. And we read these rules from left to right, again saying that if there's an edge, then there's a path. And but that's not all. We also need to compute the transitive closure to make sure that all the edges that are connected are also part of a path. And so here we say that if there's a path x set and an edge set y, then there's also a path xy. Cool. So that's a very brief description of the data log language. And I invite you to read more on Souffle. And I'm going to be describing a little bit of the material in one of the papers, one of the first papers that describes Souffle. And here I want to mention the some of the optimizations that happen in Souffle. First, it starts with a data log program. There are some high-level optimizations that are done in the declarative language, and then it gets converted into a relational algebra machine that is described in an imperative language, and there are also some optimizations performed there. And finally, there's some C++ code that gets generated, which, if we wanted, we could compile down to binary. However, we're going to be more interested in looking only at the C++ output, and so ignore compiling down to binary for now. All right, so we already described what Souffle is, but why are we talking about Souffle? Why do we think it's interesting? Well, data log is a language that is well suited for program analysis. So in particular, it is, if you restrict yourself to a subset of the language, it is not Turing complete and it's guaranteed to terminate. And so it is a nice property to know that program analysis will terminate, or programs in general will terminate. The second thing is that it manages its own memory within that section of the program. So you feed some input and you don't have to worry about memory management anymore, not even after receiving an output. So I think that's very neat. Also, the C++ that is generated via Souffle can take advantage of parallelism via OpenMP. So the C++ is annotated with OpenMP pragmas. So if you have access to many cores, then and your program analysis is written in such a way that can take advantage of parallelism, then this is an incredible opportunity. You can also have some features such as provenance and profiling, which aid in the debugging of program analysis. So provenance essentially creates a proof that shows you why the output relation exists, given the input relations. And profiling, well, it's just profiling for Souffle. And finally, it is a high-level language in which I believe all data flow problems can be expressed. And since a lot of compiler problems are data flow problems, it seems like Souffle is a useful tool for program analysis writers. All right, so again, we know what souffle is now, and we know why it's interesting. The question is, can souffle programs be part of the GCC build process? And of course, the answer is going to be yes, because otherwise I wouldn't be here. But let's go a little bit more into the details. So here's another figure on the same paper that I shared before. And it describes the flow of inputs into the data log engine. But I'm going to be modifying this graph to make it more concrete when talking about GCC and how we can integrate souffle into GCC. So first, of course, we start with an input program. In our case, it could be the C, C++, or more likely the Gimple representation of the program that we're trying to compile. Then this program needs to go through an extractor, which will generate the input relations. And in this case, it will be a GCC pass, just as any other GCC pass, which might be of interest. And it generates some input relations. And as stated in the original graph, we still need to make the program analysis and somehow feed it to a data log engine. And just to make it a little bit more concrete here, yes, we're going to write our program analysis in data log, and we're going to feed our program analysis to souffle, which will generate a C++ file. And then we can use the souffle C++ interface in the GCC pass to feed the input relations to the souffle program, to our analysis, and receive the outputs from the analysis itself back in the GCC pass. So there are some trade-offs. Souffle C++ code is C++ 17, and so you need a compiler or modifying the you either need a compiler that by default compiles C++ 17 or modify the build process accordingly. You also need to modify the build process to allow for the f-permissive flag. If you want to take advantage of OpenMP, you can compile with OpenMP. And finally, you need to allow for exceptions to happen. And so, okay, now we know how we can run program analysis written in souffle from within GCC. The question is, well, why would we want to do this? And we have our motivation, which is we are building a points to analysis at link time, and we're building it in souffle. And it's no secret that there is one benchmark in the spec benchmarking suite, MCF, that we are interested in optimizing. So in particular, there's two structs of interest. There's the struct arc and the struct node. And if we perform some data layout optimizations on them, and we have already implemented a version of these optimizations in the past, those are dead field elimination and field reordering. We can reduce the size of these structures and also improve the memory utilization of the program. So let's take a quicker look. So here, it doesn't look as good, but there's some arrows that are pointing to the fields that are going to be deleted, the next out and next in the case of the arc. And for the case of the node struct, we're going to delete the arc temp. And then we reorder them. And after that, the size of these structs get reduced from 72 and 104 down to 56 and 96 in 64-bit architecture. And you might think, well, like, what does that give us, right? And so in machines with many cores, which are hungry for memory, we can see that this optimization does perform well and scales well with the number of cores. Here, you can read the x-axis as the number of cores where the benchmark was run, and the y-axis is the normalized MCF score, where the denominator is the score where the optimization was not enabled, and what? And and the other one is the score with the transformation enabled. So essentially, everything above 1 is good. Everything below 1 is bad. Now, as I mentioned, we've already implemented this in the past, but it was not what the community wanted, and it's not what the community needed. And we agree with this. So we implemented the legality analysis using a type escape analysis, which is very coarse and can only be applied to all instances of a given type. And what we want to do is to re-implement the legality analysis using the points to analysis that can be applied at an alias level granularity. Sorry if there are any questions. I cannot see the chat, so I would have to switch slides. But anyhow, we can ask questions later. For the majority of the current implementation actually fits on this slide, but again, this implementation is less precise than the current points to analysis in GCC. The implementation that we are currently have is field insensitive and intra-procedural, so it only works within one single function. But you can see how it's a more concise implementation. It's a very concise implementation. And so here, for example, I'm just going to go over 3 rules on how to interpret this. So here we see that the points to is a tuple between a pointer and a pointee, and this relationship will exist whenever we have a pointer and a pointee, and the A is the address of operator. So so here, for example, PA just states that the left-hand side is a plain variable and the right-hand side is an address of expression. So pointer, pointee. Then we also would need to implement the case where one pointer is copied into another. And so here, these are both plain variables. I'm following a very familiar and pretty much similar to implementation than the one in GCC. So this might be familiar to some. And so the idea is that, well, if you have a pointee that is being pointed by temp, then pointer is actually pointing to pointee, because we propagate this information down to the pointee. And we also have support for the reference. S here means star. So here in this case, we have a PS stands for plain and star. So left and temp. And if points to temp if temp points to right, such as this case, then what we're going to do is basically we're creating this new virtual statement left equals right, which will get solved by some other rule later on. And so again, this is the majority of the current implementation. There are some details that I've left behind, such as the gathering of the constraints and some cleanup of them. But what I want you all to, get from this talk is that I think that Soufflé is an exciting possible new direction for program analysis. And that there, of course, needs to be some dialogue about the possibility of integrating Soufflé with GCC's code base. And we're currently working on a points to analysis to resolve some concerns on our previous data layout optimization implementation. And we've consulted some work done by others on data layout optimization and points to analysis. And in particular, we're very interested in the format paper And in the structure-sensitive points to analysis, that's kind of what we want to bring into GCC. And so if you have any questions, do let me know here. Now I have time to check the chat on my other tab. So take a look at that. And I also have some materials for some questions if those questions are going to come up. But I'm happy to answer any questions. Let's see. Cool. So anyhow, I don't know if people want to raise hands or how does this work, but that's pretty much it.
Richard, raise your hand. Richard or Tom?
So,
raise your hand.
okay, so I have a question, and
Yes.
so the souffle generated code, is that only used during build time of GCC, or is that like generated each time you compile a program with the analysis?
It's only so we only generate the C++ code once, and like it lives as a part of GCC. As long as you don't change the analysis, you don't need to recompile data log into C++.
Okay, and there was a question from Thomas Rogers.
Mm-hmm.
Thomas, either unmute and ask your question or type it in the chat if you would.
Again, I cannot really see the chat on this window, so I have to switch my windows.
I can read out any questions that appear there.
Okay. Thank you.
Okay, I think that may have been an accident. The hand's gone down anyway. Okay.
Yeah.
So, any other questions? To ask your general questions. I'm not going to start talks early, even if people are here, because we don't know who's waiting from other channels for those. So now's your opportunity to ask questions on all ranges or raise other subjects.
Well, if there's anyone, like if there's a particular question here, we can go over it. I have prepared some material there too. But I don't know.
Actually, can I ask how Souffle compares to Prolog?
Well, I'm not an expert in Souffle and I'm not an expert in Prolog, but Prolog, my like basic knowledge is that it's interpreted. I guess, well, it's a language, so I guess that the implementation that I know of is interpreted, and Souffle like compiles down this data log to C++. But maybe talking more about language features, Souffle and data log in general, in general, they disallowed the cut operator, and so that's one of the reasons why I think Souffle is able to be non-Turing complete, or it's non-Turing complete. And like again, it might not be the only reason why Souffle and data log is not Turing complete, but I think the cut operator would introduce some Turing completeness. Not 100% sure. Any other question? Or does that answer fully your question?
Yeah, I'm not an expert in Prolog either, so, but I had some experience with it many years ago.
Okay. Cool. Well, I don't know if there's not any. I'm happy to receive questions on my email, and I'll forward them to my collaborators. And
Is there an, if I may, so is there this is David Malcolm, is there an analogy, I guess, between we have, let's say, Lex and Yak for doing like grammar generators, and the code would live, the generated .c code typically lives in the source tree. So is the idea that this is a way of describing a data flow problem and then, or a graph solving problem or whatever, and then the generated code again could live in the GCC source tree.
Yes, that
That's
is correct.
basically what you're proposing. Okay, thank you.
Yeah, so it's basically that. And what I really like to not necessarily stress, but one thing that I like is that well, writing data log is a lot easier than writing C++. And so if you really want to just experiment, then it's just easy to pop into data log, change some things, and then have the implementation change in that regard. Of course, it's not going to be magic, and that's not necessarily the only thing that you're going to do, because there might still be some work that needs to be done on the C++ side, like generating constraints. But I think that these alleviates some of the work that compiler people and program analysis writers often have. So yeah.
Thanks.
No worries. All right, I think yeah, I'll I don't know if I'll step down. How can I step down? Just stop sharing.
Okay. Okay, thank you very much, Eric. Thank you also to your colleagues, Christoph and Philip, who I know worked with you on that. Mary, if you'd like to get ready, be ready to share your slides in a moment or two. So we have using the GCC regression test suite for LLVM as our next talk, which we will start in about 5 minutes. Let's test your microphone, Mary.
Yeah.
Yeah.
Hi, everyone.
Yeah, good. We can hear you okay. I think we can probably make you presenter now, and then you can start sharing your slides ready to start. You are now presenter, so you can start sharing your screen ready. But we won't start the talk till the full hour. Okay, those are showing okay. Okay, so our next talk, which is about to start, is an update on the work which has been spoken about at previous meetings about using GCC regression test suite to test other compilers, particularly LLVM. Mary has been working on that for much of the last year and is going to give us an update on that. And just for those who may be asking the curious question, Mary does indeed work for me, but she, despite sharing my surname, is not related to me, for those of you who may be wondering, pure coincidence. So this is an example of a talk very much which is designed to solicit feedback from the community. So it's a two-way thing. So please use the chat mechanisms, ask questions as you see fit to guide where this work is going. Mary, over to you.
Okay, thank you. And thank you everyone for coming. In this talk, I'd like to add to the discussion on how GCC and the GNU toolchain in general can most effectively interact with other compilers. In particular, how to repurpose the GCC test suite to validate other compilers, and by extension, LLVM. We have used LLVM as the test compiler in this project, but any other compiler like ComCert could also be tested. This project came about while we were working on a 16-bit word address deeply embedded Harvard architecture, which was very similar to another official LLVM architecture. However, it rapidly became apparent that the LLVM test suites were not quite comprehensive enough for this project. LLVM has two test suites. The first would be the regression testing, which focuses on checking the IR produced. But while this is okay by itself, you kind of want a bit more when you're testing a toolchain. You might want some, say, execution tests. That's where the second test suite comes in. But for LLVM, it requires an application and an operating system, so for a deeply embedded system, it's not quite applicable. This is where GCC test suite is so good, because it has such a huge repository of knowledge that it can be used to become the authoritative testing reference that all other compilers compare against, including LLVM. So it also has a couple different test suites, one of which is the C compile time tests, which are like 30 years old, and that makes them very comprehensive for the front-end testing. Now, GCC also has an execute test suite, which is brilliant for testing backends, but it can also be used to test things like the debugger or the libraries, or if you are using an implemented simulator model, it can also test that. So I really want the GCC test suite to be the industrial benchmark for execution testing. And for this, we have a couple of criteria. The first is to mark all unsupported or X-fail features, but at the same time, we don't want to accidentally mark a couple of supported features as unsupported and then lose those tests. We also really don't want to mess with what's already there, so we don't want to alter any tier 1 language. And it needs to be compiler agnostic, as said previously. So this talk follows on from Jeremy Bennett and Simon Cook's talks, presented in 2015 and 2018 respectively. In his talk, Jeremy discussed a method to blacklist all the C test files containing unsupported tests, but this method was rejected since it broke the second criteria. if a file contained just one unsupported test, then it would have been blacklisted even if there were multiple passing and usable tests. So instead, we came up with the method of doing feature tests. So instead of testing for a compiler, we test for a feature. How this comes into it is we look for this feature by creating a simple, very minimum test of this feature, and then adding a little handler to each file that that feature is expected in. So how do we do this? Well, let's start with VLA 6.c. This test file contains or requires variable length arrays in structures, which is not a feature that is supported by LLVM. So it's a prime candidate for this. Here are the results for LLVM, 12 unexpected failures. Not that great. So to add this new feature test, we start in the Deja GNU libraries in target support.exp. We need to create a function that returns 1 if the compiler supports the variable length arrays in structures, or 0 if it doesn't. So the function's name will relate to how we define which C test files include this feature. We use the function prototype check effective target followed by the specialized function name, in this case VLA instruct. This function will then link to the C test file VLA-6 via DG require effective target VLA instruct, as you can see in the blue box. So next, we use the function to check no compiler messages. This function will run the test and check if there are any compiler messages. If there are compiler messages, then the test fails and the feature is unsupported. The first input is the string that's used as a comment during debugging. The second variable defines what type of test it is. It can be an assembly test or an execution test or an object test. We now need a test. And as I said earlier, the test must be the minimum feature that the compiler can support. So in this case, we use this very short test. Finally, we add the DG require effective target VLA instruct to the top of VLA-6, so the second line here. We can do the same for other C files that also require VLA length arrays and structure. The new results are here. The previously failing tests have now been marked unsupported, which is what we want. So another example of adding a feature test that gets a little bit more difficult is adding one for a specific flag. Now for this, it would be, we could do a feature test just the same as we did previously, where we have each test will belong to a different flag, but then that gets kind of hairy and there's so many tests. So instead, let's do one function for all the flags. And for the example, we will be using this file, pr87929.c. As you can see in the DG options, it's got 3 flags, which will be run alongside this test. And one of them is F signaling nans, which is somewhat supported by LLVM. If you run a file with LLVM and F signaling nans, you'll get a warning message. So that would break this test, because it's not looking for warnings. So as you can see, the test is broken. You've got one failure. As before, we start in target supports.exp. We create the function isEffectiveTargetFlag. Now this will be used similarly to how we used the check effective target in the previous example. So we also have check no compiler messages as before, also testing a short int main function, and arg is used, well, arg0 is used as the flag. So as you can see, $arg is the flags that will be run, that main will be run under. The big difference between this target support function and the one we saw previously is the selected. Now that's used by the function in this file, target supports-dg.exp. Now this function will verify the number of arguments, make sure that we're getting what is expected. Now there's no point in skipping a test if it's already being skipped, so it checks for that as well. And then it takes in the selector and the verbose part of target supports.exp function, just to check that, yeah, okay, we are meant to be skipping it and that the test has failed. And then it fails, or skips rather. So here we have the final step, adding the DG require effective target flag to the file with the F signaling nans. And then the results become unsupported. So what about removing common flags? So here we have gcc-dg, which is another GNU library file. And here we can see a list of flags which each C file will be run under. So VLA-6 will be run with 00, and then run again with 01, then 02, so on and so forth. Now that's fine until you realize, okay, not every flag listed here is supported by LLVM. So we've quickly added the check effective target LLVM, which breaks the fourth criteria. It checks for LLVM. That's not quite agnostic, is it? So, okay, we need to mess around with this a bit more, but it gets the job done for now. The current results for GCC, no change, which is what we want. We haven't messed anything up. For LLVM, there is actually a big change. More passes, fewer failures, and a lot more unsupported tests, which we do expect. So as for future plans, we really want to be able to run this GCC test suite right out of the box for any other compiler. And for that, we need to do quite a bit more work. We need no more unresolved tests or unexpected fails or even unexpected passes, but we are going to expect having more unsupported tests and fewer passes than what we would be getting if we were testing just purely GCC. And our final future plan is to upstream the project. Now, I think I'm getting to the point where it seems like the right time for me to start doing a couple of little pull requests with a couple of little changes. But I want to know if we're on the right track. Like, is this the right strategy and is this the right time for upstreaming? So I'm going to do a little poll. See if it works. Start poll. Okay. I think we should have a poll up. I'll leave that up for now. And finally, I'd like to leave with another discussion. We've run into a couple of problems with variants in error messages. So there are some tests which look for a certain error or warning message, and because LLVM is different to GCC, they end up being different messages, and so the tests fail. Now, one way we could fix this, which might be the right way, is to add every possible warning or error message for that file. Alternatively, we could just find a meaningful substring and use an amalgamation of both GCC and LLVM messages. Or perhaps there might be a better way that you know of. But please feel free to discuss with me now. And thank you for listening and for voting if it's working.
Mary, if you go back to your previous slide, you can do end poll and we'll see what the answer was.
Let's see. How do I do end poll?
Wherever you started the polling from, you can do end poll, I think. So on your plus button on the left.
Let's see, start a poll. Nope.
Did you get some poll results?
Not yet. Swear I know technology.
Right, your polling options have come back up again. And I've clicked again. And you should have an option to end the poll after a bit. And then it tells you. While you're just waiting for that to try a second go on the poll, you've got a couple of comments and questions from Nick Alcock and Joseph Myers there. And Sega Bosenkul, sorry, Sega, I'm terrible at pronouncing names, also wishes to ask you a question. So go ahead, Sega, as well.
Hi. So I answered B for the poll. In my opinion, you should not try to upstream this project. You should upstream single patches to solve single problems, to make single things more generic than they are now. Those will be accepted easily and will actually improve things. While trying to upstream everything it might not end well. And it won't be easy for anyone. It will be very frustrating for everyone. So please don't. Please just send single things.
Okay, thank you.
Let's do it a little bit. Okay. Okay, so there's some useful comments here from Nick Alcock has got an optimization suggestion. I'm not sure, can you see those there, which is to, rather than testing for individual options, why not scan all the options that are used by all the tests once at the beginning and see which are available, and then you can automatically trigger only for available options in there, which will be a lot faster and simpler and would mean you don't have to change all the tests. And Joseph is giving you some feedback on the examples you use. And I think this is a good example of why actually probably submitting individual changes at a time will get you the level of detailed feedback you need. But it's also helpful because it does mean we're reviewing those tests, and some of the things in tests are there for historical reasons and maybe don't apply. So it may just not be making the tests more generic, but you may be cleaning up tests. Okay, and I suspect that may mean that you end up cleaning up tests. Certainly the example of Nohanan actually doesn't seem to actually be a problem, more in the case of the last example you gave of variant messaging. Yeah.
All right, thank you.
Any more questions and comments? Jeff Law, you'd like to raise you'd like to ask a question, please go ahead.
Yeah, first, I'm glad to see somebody tackling this problem. It's something that it is of professional interest to me now, whereas it wasn't before. The comments I would have is it looks like you've kind of built something that works reasonably well for the historical C torture suite, the compile, execute tests that are from C torture. And it almost seems like that suite is probably easiest to move and migrate. And in some ways, you want it to be kind of independent of the compiler and have a way of flagging. These tests use VLAs, and this set of tests uses nested functions, which are often not supported. And I think that's all great stuff, and it would mean a change in how the GCC developers add tests to that test suite. It means they have to start thinking about how is this going to work in another compiler suite, which is fine. There's nothing inherently bad or wrong with that. What I think is the really tough nut to crack is, as you say, the diagnostics, because those are going to be different, and I doubt we're going to get those two projects to converge on diagnostic messages. Two, a lot of the tests over the last 10 or 15 years have moved into the TreeSSA DG framework, which is testing the IR. And there's value to that. Have you guys thought at all about how to start looking at that problem? Because it's big and nasty.
We haven't thought that much about it at the moment. We're carrying on with focusing on the execute and compile side of it. Jeremy, you look like you want to say something.
I was going to say, if you go back to your second slide, the one where you showed the different test suites, I think that sort of, it's a very good question, Jeff, but I think I've now probably caused more trouble than it's worth. That's it, this one here. Actually, to some extent, so I think generically there's a question there, and it is a good question. I think for LLVM in particular, perhaps that's less of a worry, because what LLVM does have is a very comprehensive test down to the IR level, the LLVM integrated tester, and that's about 46,000 tests. So I think the real driver for us was the lack of LLVM tests for small embedded systems. The LLVM test suite is great, but it's really a set of applications to run on a big system under an operating system. So I think for deeply embedded systems, the GCC regression test and actually the GDB regression test can be used for this as well. They're quite a good way of exercising embedded systems. So that, but it's a good question, Jeff, of can you get more generic in that set of tests as well?
Yeah, it sounds like you guys are looking at a slightly different problem. You know, the IR tests and maybe where I'm looking to go are probably out of scope for you guys. And part of what I'm thinking about is how do we verify vectorization, for example, is occurring in both tool chains? That kind of problem. And I don't have a solution for it, just to be blunt. But that's the kind of thing I'm starting to think about is how do we verify performance across two different tool chains? I'm in an organization now where we are a multi-compiler company, and we want both tool chains to perform well, and we want to test for it. And we don't want to essentially be writing tests in both IRs. So again, probably out of scope for what you guys were tackling, but it is something that I am starting to think about, and I'd be very curious to see how, is there something we can learn from what you guys are doing to take us in the direction we need to be going as well?
That's a good question. I think the one thing I think we've taken away from this is test for features, not compilers. And
yeah.
The discussion here and actually understanding what exactly the features are on each test is good. Is a good thing. I see, Joseph, you've raised a question. You have a related question, so this is for anyone to answer. Any thoughts of using the glibc test to test other libc implementations? And that is a very good question, because I think glibc has by far the biggest set of C library tests out there, and that's a very good point. And what are the challenges, for example, of trying to use it to test newlib, which is a much simpler C library? How do you deal with that? Joseph, do you have any particular, have you got any answers in working on that one? Okay. So I think that thank you, Sudesh. That's useful to know. The comment that some tests that use glibc in internals, but it shouldn't be an impossible task. So I think, Mary, when you finish this one, which has been going for 6 years, maybe you've got another exercise to come along, which is to do the same to get glibc to test other C libraries. Good idea.
Yeah, sounds great.
Okay. Any more questions or comments? Okay, well, thank you very much, Mary. I'll leave you to stop sharing. Our next speaker will be Sergei Makarov. And Sergei, I'm not sure if your slides are already up, in which case,
Testing.
Sergei, we can hear you.
2020.
So we can hear you fine.
Okay.
And we can see you as well.
This is a test.
Yep.
Can you hear me now?
Yep, that's clear. Yep. We're just a couple of...
Sorry about the sound issues. Can you hear me now?
Yes.
This is not very good. We have about 2 minutes. Yes. Yes. Okay.
So our next talk is from Serhii Makarov. We do try and group the talks together, so this is I think a good follow-on from the previous talk about testing. And Serhii is going to look at analysing historical test results. So Serhii, it's all yours. Away you go.
We're unable to hear. Sorry.
Serhii, there seems to be a problem somewhere. Some people can hear you and some can't. And I could hear you at the start and now it's disappeared. You might want to try dropping out a big blue button and coming back in again. It has been known to drop connections occasionally.
The chat is definitely useless for interaction. I mean, the log is huge.
Yeah, I think we need to avoid using chat for today's session. If anyone has any questions, if they either raise their hand or put their webcam on, we'll go to you as best we can. If not, please feel free and email me. I'm regularly checking them, so if need be, I can forward them on.
Okay, I'm testing now, and I'm testing my webcam again.
We can hear you this time.
Okay. So with that slight diversion, so we have a tools project that depends a lot on other system components and has a small development team. And although we are fairly robust to regressions causing fatal errors, because system tap infamously depends on internal kernel interfaces that the kernel provides no guarantees of stability for, we've engineered around that to try and fail gracefully as much of the time as possible. But for various functionality, non-fatal degradations tend to creep in over time. The same with working with debug information. Debug information is a fairly loosely maintained area as well. So that's another subject where it's possible to have things change over time. Let's see. So in this talk, I'm going to make the argument for why it's useful not just to set up a CI system, but also to maintain and curate a historical archive of test results. I'll give an overview of the toolkit I wrote to do just that for our purposes, And I'll give some examples of the types of analysis that you can do if you have historical data, as opposed to just the most recent results from your CI system. So to give an overview of the problem, why would a project want to keep a historical archive of test results? I've looked around at projects setting up continuous integration, and the standard blueprint is that you have proposed patches coming to the project, so they're not yet in your project's Git repo. You automatically test them on something like a set of build bots or a Jenkins server. You compare the result to a known good version of the project, so you assume that a recent version of the project is good enough for your purposes, and you accept or reject the patch based on the results, whether they contain any regressions. So obviously accepting it just means that you pass it on further to manual patch review. But at this stage, based on the test results, the accept or reject decision is very basic. If the test suite is complex and large and has test cases with unpredictable results, then you're probably only using a subset of those for the decision, and you don't really store the BuildBot test results for over a long period of time. So the systems I've seen generally keep about 2 months of data, and beyond that, it probably gets to be worryingly large to keep all of those raw test result logs. And this system works great, and it solves a slightly different problem from what we have on our project. This is great for projects that have a fire hose of incoming patch submissions, and they want to cut down on the maintainer time that's spent on reviewing those. So that in addition to this, can such a system guard against regressions creeping in long term? Well, it could if we assume several things which are unlikely to hold for some projects. First, we assume that we have a very clean and disciplined test suite, so it doesn't give us spurious failures that don't correspond to serious problems. And it doesn't have non-deterministic test cases that give one result one time you run it and a different result the next. And we assume that the continuous integration, the collection of build bots we're using, covers all relevant system configurations. So if someone has an exotic hardware architecture or distribution, then whatever regressions their system experiences are going to be left out of this process. And finally, we assume that regressions aren't going to be caused by changes in the underlying operating system or other dependencies, because those changes aren't being captured by the patch submissions we're accepting or rejecting. This may not be true for some projects as they are now, so there's kind of a spectrum. My vague impression from what I know of all these projects is that GCC, for example, has a very strict and disciplined test suite. They don't really have non-deterministic test cases, nor do they need to keep them around if any show up. GDB and SystemTap are on the opposite extreme because they interact in slightly different ways with underlying operating system features that have very intricate behavior, and likewise with debug information. And also the test cases often involve parallel code, which can be set up and end up running unpredictably in terms of the ordering of events. glibc in terms of engineering efforts and in terms of the need to have some test cases with the test non-deterministic functionality strikes me as being somewhere in the middle. So for the projects that have very messy and large test suites, it's not going to be feasible to just sit down and fix everything and make the test suite work at the same standard as GCC all in one go. So for that purpose, instead, what I started trying to do for the SystemTap project is to just collect all of the BuildBot data, put it into a central repository, and then see what type of analysis I can do on it to try and discover what the trends are and what we could focus our attention on. Okay, so just a quick check up to now. Hopefully people were able to hear me all right. Sorry, that initial technical difficulty kept me a bit worried. Okay. Anyways, so continuing with the talk, the toolkit I wrote, I presented on a very initial idea for it about 2 years ago at GNU Cauldron in Montreal, and the basic idea is still the same. I have our system tap build bots producing Deja GNU test result logs. I parse those and produce them into a slightly more analyzable JSON index, which contains the same information. And I store the test results and JSON index in a Git repo. And what Git gives us is that I don't have to worry about keeping 2 or more years of logs in one place, because these logs are going to be deduplicated with a relatively high compression factor, which holds up as you add more test runs over time. So these test result logs are mostly the same results appearing over and over again. So deduplication is a good compression strategy. Bunsen also includes a Python library for querying the index test results. And what I'm talking about today is the various analysis that can be used to extract information from the repository using this library. So in order to describe what type of analysis I can do, I have to go into a bit more detail about Bunsen's data model. So every time we invoke our test suite and put the results into a Bunsen repository, the metadata associated with that is a pair of commit IDs, a description of the system configuration that ran the test, and a list of test cases. So the 2 commit IDs, and it's important to distinguish those because it's possible to be confused otherwise. First, we have the git commit ID of source code of the actual project we're testing. Now, this is peculiar to SystemTap because we don't do CI gating. Instead, we're testing commits once they've been committed to our master branch. This could be replaced by the ID of a submission to a CI system if we're testing patches before they end up in the repository. And we could replace this by any other version data that allows us to sort project versions chronologically and figure out which version is based on which other one. Besides this, we have another commit ID, which is the git commit ID of the test result logs in the Bunsen repository. So we have access to the original Deja GNU sum and log files if we want to do additional parsing on them. And we can also add auxiliary log files. So for SystemTap, I find it useful to include a file of system diagnostics and the dmessage output from the kernel, since that can capture information about failures that aren't obvious from the logs from running the actual SystemTap script. In addition to this, the system configuration is a set of key value pairs. Most commonly, we describe the Linux distribution or other operating system we're testing on and the hardware architecture. But it also makes sense to include versions of dependent components like the kernel or in some cases, the C compiler might be relevant if we're looking at something that depends very heavily on the details of how GCC produces dwarf. We might include an elf-utils version, things like that. In addition, we have the actual data for the individual test cases. So we follow the Deja GNU format of having a relatively small number of large test cases. So these have a name, and within each large test case, we usually have myriad subtests. So which top-level test cases exist within a Deja GNU test suite is fixed and predictable. So if it has 454 cases in the test suite, those same 454 cases are going to be run in every invocation of that test suite. But the subtests tend to present a problem. So the subtest is identified by a string which is not necessarily in many test suites unique or stable or detailed. It's more like a diagnostic message. So the model we use is that for each top-level test, we have the set of passing and failing subtests associated with it. And what we usually care about is the set of failures and comparing which failures exist in that set versus in one test run versus in other test runs of the same test suite. So we see if that set increases, decreases, stays the same, and we consider that to be our regression. And then we have the outcome, which is pass, fail, and other similar outcome codes defined by GNU. And we have various options for how detailed or compact we want this data to be. When I set up the system tab Bunsen repository, I was worried about how much space it would take up. So I introduced some compression, which consolidates any passing subtests into one entry. So if we don't have any fails for a particular test case in our test suite, we consider the absence of failure to be no problem, and we don't bother with keeping detailed index entries of the individual subtests. But other projects may not fit that definition, and it would make sense to store all of the subtests passing or failing individually. So we do include that option. Now, previously when I presented about Bunsen, I described the repository and outlined this format. And I gave as an example of analysis that you might want to do on this repository, that you could take any pair of test results and diff them. So this was modeled on many existing simple and successful utilities for diffing a pair of GNU test results. But for the type of investigation I was going to do, it actually turned out to be not particularly useful. So if you take a version of your project that has a chaotic test suite designated as known good and diff against it, you don't really get a full picture of what's going on. You don't have a known good version of your project with a clean test suite. So the baseline you're diffing against has its own problems that you might end up masking this way. You might get regressions on configurations that aren't tested as regularly as others, which also creates difficulties for interpreting a diff. And most fatally, regressions can be changed by changes in underlying dependencies. So to make sense of all of this, we end up needing the entire historical context of a particular regression and a particular test case. So the way to do that, for the starting point, I used an approach that was originally developed by Martin Cermak at my company, which is to take each top-level test case in the test suite, take each system configuration, and for each commit in a range that we're interested in, say the previous release up to now, just draw a grid with plus, minus, and question mark depending on whether the test case outcome for a given combination of configuration and commit is pass, fail, or was untested. And we output that as a table, one table for each test case. And it looks something like this. So over from left to right, we have commits with more recent commits on the left and less recent commits on the right. And from top down, we have the different system configurations that we've been testing, and we have test results inside cells of the grid. And in this case, we can see that there was a block of 4 commits that was pushed, and it introduced a very clear regression in this test case. So looking through this, we can spot it very quickly in a visual way. But the problem is that there's 454 of these tables that I have to look at to get a sense of what the state of our test suite has been over the past release. And that's a lot of scrolling. So to improve this, I took this grid data as the starting point for additional analysis. So I assembled the grid exactly as shown on the previous slide, with the key being a tuple of test case, configuration, and project version being tested. And inside the values, I put a set of the test cases in each cell of the grid that were tested on that configuration of factors. And then I scan these grids in chronological order and try and use the entire history of that row of the grid to decide if a particular change is noteworthy and worth including. And then I create a timeline view based on that. So as a detail, which for time I won't go into much detail. So again, the basic starting point for the analysis is a three-dimensional data structure with versions along one dimension, test cases along a different one, and configurations along a third. And building this is slow, but tolerable if I use the current Git plus JSON representation as a starting point. It takes about a minute for one release of SystemTap project. For a longer portion of history, it'll take more than that, proportional to the number of commits. It could probably be improved if by adding some form of caching layer, but it's not a very high priority. Getting the analysis result back in a minute seems relatively fast for me. Now, the crucial part of how this data structure is represented is that when we're analyzing the grid, and I'll come back to the slide where this is visually visible. So our BuildBot system doesn't really have enough computational resource to do enough tests to fill in every cell of this grid in a timely fashion. So depending on the look of the draw, we may have gaps. And so for analysis, it's important that when we're comparing adjacent results, that we can skip smoothly over the gaps. So the data structure includes indexing to make sure that we can find the previous tested version of each test case in each grid cell. So when we're comparing across these two versions, we know that in this block of commits, there was an immediate change. And what we do with the filtering is generally try to cut out periods when the test case was flipping back and forth. So we designate those periods of time as flaky and consider them as during that period of time the test case was in a consistently unstable state. So if we have a test case that was consistently passing, then flipping back and forth, and then failing, or vice versa, then we identify essentially two changes in the test case state, as opposed to one individual change for each time it flipped back and forth. And there's several different ways to display these changes. We can display them by commit and try and figure out what changes were associated with each commit that we made. And we can instead sort them in chronological order by test case. So at the moment, neither of these analyses is perfectly clear just from reading these tables, but it works well enough in conjunction with having the grid view to come back to and visualize what the test case result is like. So another analysis we can do is to find the origin of a regression. If we're interested in history of a particular test case, we can turn off the filtering and just examine every change in chronological order. And that's just a straightforward modification of the algorithm described on the earlier slides. And another analysis that projects might find interesting is to use the collected data in the repository to identify flaky or non-deterministic test cases. So in our case, It's happened often enough that the build bots test the same commit more than once for one reason or another, that I have enough data to do this without having to do repeated testing additionally. So out of several thousand commits at this, so out of a few thousand commits at this point, well, not a few thousand, out of a few hundred commits at this point, there's around 300 where I have duplicate test results, and I can use those to identify non-determinism in test cases. So here, the basic algorithm is that for each combination of commit and configuration, we find we check whether it was multiply tested, and if it was, we check whether each instance of that test case produces the same set of failures, or if there's a difference. And if there's a difference, then we straightforwardly flag it as non-deterministic. But there's actually not that much complexity to this analysis once you have the data all in one place. And let's see, yeah, so I hoped to share my screen at the end to show that particular script, but I'm not sure in terms of time constraints. I'll give my conclusion briefly. So having the historical data lets us have some clarity about the state of the test suite. If we're just looking at the latest two sets of test results, then we don't know which failures have been in the test suite a long time and were just overlooked due to lack of developer resources, and which failures are recent, and which failures are important, and which ones are unimportant. The toolkit I have works well enough for our purposes. There's quite a bit of development work. I'm planning to make it more adaptable to other projects. We have some interest from GDB developers in terms of adopting it. And I've listed on the slides some ideas on things I'm planning to improve. In terms of projects I'm aware of and what their testing situation is, for System Tap, we have, and GDB, we have working parsers for getting data into Bunsen repository. Our continuous integration for System Tap is active, and there used to be a very solid continuous integration build bot for GDB, but due to maintenance degradation, it's gone defunct at this point. And the archives from that are, from about a year ago. For glibc, I'm aware that the project is currently setting up a CI system. I don't have a parser for glibc logs yet, and I've put a link to the glibc project's description of their CI system. It's definitely a system that's focused on solving the patch fire hose problem first. For GCC, as I mentioned, GCC has a much more disciplined test suite, which doesn't immediately benefit from this type of analysis. But it is worth noting that the Jenkins server is active and well maintained and produces a large fire hose of data. So in terms of where I'm planning to focus my efforts, it's going to be to keep improving the analysis I can do for System Tap and to support the GDB people in applying Bunsen to their project. For working with other CI systems, I would need to figure out a set of best practices for how to extract data from a continuous integration server on an ongoing basis that doesn't require as much maintenance as it currently does. And in terms of that, that's pretty much it for my talk. I've listed some links on this final slide, and thank you for your attention, and apologies for the unexpected sound difficulties.
Yeah, hi. Thank you very much indeed for that. Very useful talk. Any questions or comments from the community?
Yeah, it's worth noting that I'm also having no luck with the Matrix chat. So Either
Okay.
people could raise hands or
Jose.
Hi, Sergey.
hello.
What is the user interface for this? I mean, imagine that we set up for gcc.git, for example, we have a continuous integration that runs tests like every week or every couple of days or every day.
Mm-hmm.
And then it creates a repository with the historical data. Now, how will that help me, for example, to bisect a problem for which I have a test identified as the one that is failing?
So currently for System Tap, we do all the testing internally. So we have two ways of accessing the data. The first is a very rudimentary CGI server, which you put in a URL and it runs the script and returns the analysis results similarly to what I showed on the slide earlier. And the other option for accessing it is logging into the machine and running a Python script to get that result. So probably the most robust solution is for these grid views, which are actually global to the test suite. So you don't need to select a specialized query. These would probably make sense to generate statically and put somewhere on a web server just as HTML files. So I'll probably develop more sophisticated web interfaces at some point because I've had some good suggestions from key sites on how to do that. But I'm keen to preserve the ability to generate static HTML files and just have a batch job generate those and put them somewhere.
Okay. Thank you, Jose. A question from Aaron Sordi. Are Sarah's slides posted somewhere? If nothing else, they will appear in due course, I hope, via the GCC wiki. That should be by a link into LPC's infrastructure. But shortly after this conference, they will appear. And Sarah, I'm not sure, I think we've already got your slides, but if you haven't sent them to Sarah, please do. And we'll make sure one way or another the slides are made available.
Yeah, so the copy I'm presenting from now is the one I sent. So yes, I believe you have them.
Good. Thank you very much indeed. Okay, we have a 15-minute break now, and then we'll come back after the break with a talk on dwarf extensions from Tony Tai and Zoran Zaric. The second session of today will, I hope, be chaired by Joel Brobecker, who I'm sure is about to join us on here and will take over the chair for you. So thank you very much to all our speakers for this first section and getting us off to a flying start. And I'll be back with you all in just under 15 minutes. Thank you.
Sergey, are you in IRC?
So I wasn't sure what the situation is with the IRC bridge to Matrix, or where people are currently chatting.
In OFTC or I don't know, somewhere.
Yeah, so I'm in OFTC System Tap.
Okay. See you there.
Yep. 1 second.
Hi, this is Tony. I just wanted to check this actually is working okay.
Yeah, I can hear you and I can see you.
Same here. All right, 1 minute until we start the next session. Thank you, Sarah.
Hi, this is Tony.
Hi, Tony.
Hi.
Are you the only presenter, or is Zoran going to join us today?
Yes, I'm the only presenter, but Zoran is here today with us.
Excellent.
Pedro and other members of the.
All right. Well, it is 15:15. So Tony, thank you first of all for doing this presentation for us. So you'll talk about dwarf extensions in the this specific context. So when you're ready, I'll leave the floor to you.
Okay. Thanks very much. So this work we've been doing as part of the AMD open source debuggers project, and I've got a few links here. They're at the end as well. And our goal really has been to get heterogeneous computing debugging to kind of be viable. And the thing we had to kind of wrestle with is the fact that GPUs do have a bunch of kind of novel things. They have multiple address spaces, which are kind of hardware supported things with different instructions to access them. They have a lot more scalar registers than traditional CPUs have. And then they have these interesting wide and many vector registers. And the big thing about the vector registers is the hardware will execute instructions in a SIMD-like manner. And we get the compiler to actually map our source languages where a thread of execution of the source language is kind of using a single lane of the vector register. The vector register has many slots. And this means that if we have a variable that takes up more than one of those slots, we have to actually kind of spread it across that slot of different vector registers. So we've got the difficulty of describing variables that kind of span pieces of registers. So our challenges were really that more often than the time, we end up with variables being spread across bits of different kinds of storage. And we've got these pieces of registers, we've got these different address spaces. And then we got this SIMT execution model where we want to kind of select which piece of a register we want through a runtime expression rather than just being a static part. And then the other thing that kind of happened is we got a lot more complex expressions, and there's a great deal of benefit in being able to factorize the creation of the location descriptions, which isn't kind of possible currently, and which ends up in duplication of the expressions. So the things we kind of ran into with Dwarf 5 that kind of made this difficult was we couldn't really describe variables that are on parts of registers. Neither statically can you talk about a part of a register or the runtime index. And that some features really only work when the memory is the when variables are located particularly in memory, such as there are type attributes which describe the object that they're going to work with, but you can only describe that object using its memory address, which isn't helpful when it wants to sit in a register or some permutation of registers and memory. And then we have the problem that, if we wanted to use dwarf procedures to do factorization, they only accept memory addresses. We can't describe the vector register types because they're much wider than the base types that dwarf provided, other than just thinking of the pile of bytes. We couldn't create memory locations for particular address spaces, and then CFI had problems with it only accepted certain kinds of locations, didn't accept composites, couldn't accept address spaces, and then we couldn't deal with bit fields. So we wanted to kind of try and tackle all of these problems kind of in a reasonable manner. So we explored a bunch of different approaches, and the one we ended up kind of landing on seemed to be the simplest and provided us with the most benefits. It's really based on generalizing the execution model and providing a bunch of composable and constructible operations on that slightly different address space. And what we ended up with was a small number of operations we had to add that composed generally. And the alternatives we looked at ended up with a lot of specialized operations with special rules and context-specific semantics that were just much harder to deal with and for compilers and debuggers to work with them. And I think the major aspect is really that we're going to allow locations to be on the stack. And we'll talk about, well, what do we kind of mean by that? So our main goals really were we wanted to have an upstreamable GDB and LVM compiler and GCC compiler support. We wanted to have it so that we could support other tools such as the Total View debugger. We wanted to be definitely compatible, backwards compatible with Dwarf 5. Obviously, we wanted to have the things that GPUs needed, but we didn't want it only to benefit GPUs. We believe that the changes we're kind of suggesting here will benefit other things beyond GPUs. So just a quick, what is Dwarf? Well, it's really a standard way of specifying debug information. It's really describing how a source language entities, compilation units and functions and types and variables, how they map onto the physical hardware that the compiler decided to generate code for. And you embed it in the code objects, or you can split it off into separate files. You can answer questions like, this program counter, what's the source line? Or for this source line, what's the program counter? Or, where do functions start? Or where are source variables located? Are they in registers? Are they in memory? Are they in a combination of both? And it allows you to kind of virtually unwind the call stack so you can kind of get a view of how your program was running. And the big thing, one of the parts of it is that it really it wants to describe a big diversity of how locations of entities, where they are. And those locations could involve runtime calculation, like the current value of the stack pointer. And there really is this big diversity of where locations be, registers and memory. Maybe they got optimized away and we know what the value is, or maybe they got optimized away and we don't even know what the value is, or they're spread across a lot of those places. So consequently, Dwarf really has this rich expression language where expressions are basically evaluated on a simple stack, one operation at a time, in a particular context. The context kind of says whether you're trying to get a value or the place something resides. And, that context also tells, what program count you're at, or, so for some things, we actually need to know what an initial value to evaluate the expression within. And some of that context really comes from where the Dwarf expression is residing. A particular attribute is for the purpose of computing a value, or is it for the purpose of computing a location of something, or maybe there's an initial stack value. So to try and go through a bunch of simple examples here, this is how Dwarf 5 currently works. So the simple example here is we've got a source program that wants to have a dynamically sized array, and the size of that array is 42. But the compiler has optimized this. For example, maybe the value was, at a certain point relative to the stack pointer, or STPR, and we want to dereference that stack pointer to get to a memory location and read the contents of that. So this is the Dwarf expression that kind of is going to achieve that. In this case, we're trying to evaluate this expression as a value. So that's kind of part of our context here. We're going to evaluate it on the stack. Here are the instructions we're going to evaluate, one operation at a time. So the first operation here is going to read the contents of a value. So we're going to push on the stack here the value. Notice that every entry on the stack, we've got a value and its type. The type has to be a base type as defined by Dwarf, which basically tells you what the size of the type is, what its encoding is, is it a numeric or a floating point, and it's byte ordering, for example. So in this case, I've now got the value of the stack pointer. So the next thing I can do is I can dereference that, does the obvious thing, reads its context. Now I've got the 42. The result is a value, so the top value of the stack is the result of the expression. So if we look now at, say I want to say the location of a variable. So suppose I've got this variable here, and on a machine, the compiler decided to put it in this scalar register here. So in this case, my context, I'm evaluating in terms of a location. I'm going to use the word location. The Dwarf spec talks about these as location descriptions. That's a little bit of a mouthful. So here, my first operation evaluates to get the location of a register. It gives the name of or the number of the register. The interesting thing here is Dwarf doesn't evaluate locations on the stack. It has this separate conceptual location area here. So what we end up with is saying we're in a register here. And since we're evaluating context for location, then the answer is what's in the location area. So let's get a little bit more complicated. Suppose here we've got a variable, and it turns out that that variable was allocated in a scalar register, but for some reason, in this particular program counter, the compiler spilled it into memory, which is accessible, at an address plus an offset. This might be, the address of a stack pointer. So we're going to start off reading the value of the register again. So we've got that on the stack now. So next thing we're going to do is we're going to add our offset to that to get to the location that we want. Then we're at the end of the expression. We're evaluating it as a location, so Dwarf conceptually implicitly takes that stack value and turns it into a location description, taking the value as if it were an address. And then that's our final answer. Sounds like Jeopardy. So let's get a little complicated here. So here I've got an example where I want a location. The variable is made up of a piece that's in a scalar register. It turned out that a piece of it was the compiler optimized away and was undefined. And then a piece of that register is actually in memory at a particular offset from a stack pointer. So I've got to take my stack pointer, I've got to indirect through it, I've got to offset it, and that's a piece. And I want to kind of describe this. And what Dwarf has is the notion of a composite location made up of one or more parts. And each part is going to say how many bytes big it is, coming from whatever place we say. So first step, we're going to take the scalar register. So we got that in our location area. The next thing we're going to do is we're going to create a composite. So there's this piece operator. The first time you use it, it actually creates a composite. As we're going to see in a minute, as you use it subsequently, it's going to add parts on. And it's going to take its first part, if the location stack has a location on it, the register. So now we're still in the process of making the composite, so it's incomplete. Our first part is going to be the register. And the for says, well, how many bytes of that register are we going to include? Next thing we're going to do is we're going to add another part. In this case, I have nothing on the location or the stack. So what Dwarf says is that's equivalent to adding an undefined part. And again, we're going to say how many bytes it is. So we've now got two parts of undefinedness. Then the last thing we're going to do here to complete our variable is we have figured out that it's a memory address of, we're going to get our stack pointer here to read it. We're going to dereference that and add the 10, we're going to add the 10 to it, and breg is an operation that basically reads a register, adds a value to it, pushes a value on the stack. So then we need to now add that to our composite, and then again, Dwarf says that, well, I want a location, I've got nothing in the location area, there's a value on the stack, and it's going to interpret that as using it as the memory address of that location. So now we've got our composite, we've got all the three parts of it. So then the last thing we do, we're at the end of the expression, so that now makes that composite complete. So what if we wanted to offset that composite location? We saw with a memory address, we can just use the add operator. Well, can we use the add operator with composites? So suppose I wanted to offset this by some amount, like 5 here, a little bit artificial here, but just suppose I wanted to do that. If I took that previous example and said, well, can I just do an add to it? Then the answer is no, because add only works on values, and locations aren't values, they're in this location area, so they're separate. So if the compiler wanted to do that, it would actually have to build a location which is just the part it wanted, and maybe we could build a composite using this expression to achieve that. But the observation here is that we don't have operations that kind of naturally work across these two divides. We've got the stack and we've got the location. So this really kind of led us to think about, well, what actually is a location? And a good way of thinking about it is that a location is really referring to some location storage. And you can think of location storage as just a contiguous linear organization of some set number of bytes. And you can think about all locations being this way. Global memory is a linear organization of this number of bytes, which is the size of the address space. A register, each one of the registers is a linear stream of bytes, which is the bytes that make up that architecture's register. Even composites, you can think of just being a location, a storage location, which is the bytes made up of all its parts. We didn't kind of show an example, but Dwarf also has the ability to talk about memory, a value located in a where we don't know where it is, but we know what its value is, and it's an implicit location. So you can think of that as a stream of bytes. And then the undefined location is really just an infinite size location, which has every byte being undefined. So what this leads you to think about is that a location is really composed of what kind of location it is, a reference to its location storage, and then a zero-based offset. So if we think about that, a location could be put onto, if we could put a location on the stack and add new operations to work with that, then, for example, we could have an offset operation which updates the offset to a location to where you want. So now we can also modify existing operations to say, like, for example, deref operates by popping a location off stack rather than an address value and reads it. And so this means it will work with any kind of location, not just memory. And we can define some implicit conversions to make this all backwards compatible. So the key part of the extension is really making locations appear on the stack. And all dwarf 5 expressions then evaluate unchanged and give the same results. And this then allows us to get greater expressiveness. So if we take that view and start looking at some of those examples we had, we notice we've got no location error now, we just got the stack. So this example, we've got a variable which maybe it was existing in an SGPR, but maybe the compiler spilled it to a particular slot in a vector register. So this is something we can't do with current dwarf because we can't talk about a piece of a register. So what we're going to do is we're going to start off, we're going to get our register, and then what we can do is use our offset operator, and it's just going to update the offset of the register on the stack. And we can now, oops, sorry, one too many. And then this actually is now our location here. So this we can't do with current dwarf because you can only talk about the beginning of a register. And we could maybe solve this by making all of our big vector registers have lots of names, but this becomes rather intractable. There are so many registers on a GPU that this would quickly become intractable. And even if we did that, we still couldn't do any runtime indexing. I mean, this is a static index. Our next example will show a runtime index. So doing this gives us that composability. So this example, we've got the SIMT example where we had a SIMT value which is spread across 2 different registers of their particular lane. So we're going to take our register, we're going to put it on the stack. We got this lane operator. We're evaluating a context where we know we're at lane number 0. It depends, or lane number 5 here, depending on which lane our debugger was focused on. So this then gets us our 5 on the stack. Our slots are 4 bytes big, so we've got to multiply them by the 4, and that then gets us to our byte offset of 20. Now we can apply our offset operator, just like we did before. This can be the first piece of our operator. We kind of have the same rules as the piece. We start off first use makes a composite, and then we subsequent ones make offsets. We have a few conversion rules, which is the same thing that current dwarf does to get the backwards compatibility. And now we can move on to our second part, is a second register. We can get our lane offset, multiply it, get the offset, add it to it. And then finally, that is now our complete thing. So now we've got a composite that describes the 2 parts of the register there. And then we've got our composite being complete. So we made it a little bit more complicated. Suppose we took a previous example, and suppose the compiler spilled part of that register, the 2 registers to memory, and another part maybe it knew what the constant value was. So here what we're doing is we can have our memory address. So here we've now letting addr return a location. We can add that piece to our register. We can now take a constant for that. Again, we can create an implicit location for that. So again, implicit's now our locations rather than in our location area. We can add that piece. And then finally, we did add an operation to explicitly end a composite. And the advantage of this is we can then build composites midway through as well. We're going to have multiple composites being built on the stack. Didn't really need to do that in dwarf 5 because you can only build them as the last thing. So this now has got a composite describing that example here. So address spaces were the other thing we needed to deal with. Now we've got locations as this thing that can be on the stack. What we can simply do here is, although dwarf 5 does have an xdref, it doesn't really give you a way to actually build an actual address location that is in a locus area, and you can't compose it into composites. So what we're going to do is here we've got an example, we've got a variable that's in a particular address space. On a GPU, it's common that the stack pointer points not to our regular global memory address space, but a per lane address space that there are special hardware instructions for dealing with. It has swizzled memory so that each lane sees one linear view. So what we're going to do is our stack pointer points to this separate address space. Again, we've got an offset to get to our variable. So we take our register that we want. We can read its value. There's our stack pointer value. We can talk about our address space. In this case, address spaces, are architecture specific. Our one here is our per lane address space. We can then use this new operator to form an address space. So this builds us a location that takes the address value and the address space and builds us a memory location. So now memory locations just have this extra property that is their address space. And so that then becomes the result of our expression. So, and we can compose this so that anything that takes a location can now suddenly deal with locations that have address spaces. Bit offsets, similarly, we can just extend the idea that since locations have offsets, we can think about an offset as just not necessarily just being a byte offset, but being a bit offset. So in this example, we could take a register, we can then get our bit offset, and this could perhaps be a runtime calculation. And then the new operator here, we've got bit offset as opposed to the regular offset, and this now gives us the bit offset. So now we've got our little slice of the register. Again, something that current dwarf, although there is bit piece, it really only works with composites. You can't kind of do it in other locations. Other benefits we have, once we have locations generalized on the stack, there are other places where dwarf says the expression is evaluated starting from a value that's on the stack, or it has this push object address, which uses a context, which is the object address. And currently, we can only think about those as memory addresses. Since locations can now be on the stack, we can now think about these things with things in registers or in composites, which is really helpful for GPUs because the compiler tends to put things in memory and registers and composites them a lot. It also means that the call, which dwarf has to call dwarf procedures, we can now use that because we can have locations of any kind to be on the stack, and we can pass them in and out through the call. And again, that benefits us to get this incremental increase, building up of the dwarf expression. So CFI, similarly, now we've got locations as generalized on the stack, and we needed for the GPU to talk about CFI where things were in address spaces or in composites. We've seen how registers could be spilled into multiple pieces of registers because of the SIMT work. So that generalization allows us to deal with that. And then the other thing we kind of added is on GPUs, for example, as we call a procedure, it might be that we only spill registers, that are callee saved, if the exec mask, which controls which lanes are active, are currently showing that that lane is active. So we want to actually conditionally, when we're unwinding the stack, virtually unwinding the stack, say, well, if a bit in this register is a 1, then get it from here, and if not, get it from somewhere different. And then that meant we also needed a way to get the value of the exec mark as it came into the procedure so that we can actually use that as part of the expression. So we added operations to deal with that. The bit select here is really just something that composes with building a composite out of location descriptions. And then the final thing we kind of did was for multiple places, Dwarf 5 introduced has the concept of location lists, and you can use these for implicit pointers and calls. They can refer to a debug information entry that has a location list. So we extended the idea of a location to not just be that it only had one thing. We allow it to have a list of single locations. So for any particular location we have on the stack, it might mention that it's in more than one place, which really mirrors what location lists are. And then we extended the operations so that, for example, the offset operation does an offset on each one of those multiple places it can exist. And Dwarf 5 kind of defines operation expression location lists separately, which is fine for Dwarf 5 because it only allows you to build that location list as the last step of the expression. And by generalizing, we really now can allow location descriptions to kind of be built midway through. So this kind of naturally fell out that we could now unify those. This is just a summary of the new operations we added. I think we talked about most of these. In CFI, we added a couple of things for address spaces, and then we have some attributes we kind of added to support vector base types. And then we built on that to do our divergent lane control. Didn't really talk too much about that, to have attributes to support that. Our current progress is that in GDB, we've kind of got an initial implementation that Zoran's done in that, and Pedro's been working on that. We're also currently working on LVM compiler support, and Total View is doing implementing this to see how it works out. Mentor Graphics is working on the GCC part. I think Andrew Stubbs is going to do a demonstration of that on Thursday, I think. You can see the full description of what these extensions are, and then this link is to this is kind of the normative description of it, and then this gives us our AMD GPU architecture for it. Really would like to thank a whole bunch of people that helped us get so far. Thanks to GDB maintainers. We've been working with ARM and HPE. We're talking with Marcus at Intel they're working on GPU debugging as well. And also working with Lawrence Livermore Labs and Oak Ridge Labs and Mentor Graphics, as I mentioned. And big shout out for John Del Signor, who we spent a lot of time working with to try and figure out where we wanted to go. So in summary, the dwarf expressions, we've generalized them to our locations on the stack. We've got some new operations that are composable, consistent, backwards, and compatible. We've got the support we need for GPUs, but we also believe that they support other things beyond GPUs, such as CPUs. And that gets us to the end.
Thank you very much. That was fascinating. Anyone has any questions? Richard.
Yes, so if the register file were available in global memory, what's the issue with the dwarf expressions not being powerful enough to be solved if you express all these as addresses of that memory region?
Well, if it's in, yeah, I mean, you could then just use the memory address and everything would be copacetic, yeah.
So like if you introduce a magic global GDB rex symbol that the consumer then just maps to the registers, you could express at least the location expressions via such trick?
Yes, you'd have to come up with a way that you would want to have some magic memory. Presumably you'd have to carve out these addresses can't be used for regular memory. So I guess you'd have to maybe have a bigger address space than you would normally, because your normal address space might span the entire, address space. So yes.
We have 2.5 more minutes for more questions. Going once, going twice. All right, so to the gentleman with the beard. Thank you very much, Tony, for your presentation. Like I said, it was really fascinating, at least for me. I kind of follow dwarf, the evolution of the dwarf. So, I look forward to seeing this in action, and then maybe making it to the standard.
Thank you.
All right, should we get ready for the next presentation, which is about CTF and BTF? So who's gonna take lead on that presentation? Is it Indu, David, or Wayne?
Yes. I'm checking my connection.
Awesome.
Do you guys hear me?
No, but we can hear you.
Okay. Yeah.
Maybe you used the wrong webcam, maybe.
Oops, no, it's off.
There we go. All right, Indu, how are you?
Good. How are you?
Very good, thank you. Well, thank you as well for being here with us. If you're ready, I leave the floor to you.
Sure. Yeah, I can start.
All right.
So yeah, let's talk about. I have my own echo. Hello. So let's now. This there is echo.
But the sound is good here.
You don't have any speakers, right? But just a headset?
Sorry, I missed that. I don't know what I can do here. There's still some echo.
Well, if it's not too annoying for you, I think you can just go on because the sound on this side is good.
Okay, I'll try this way. At least it doesn't bother me so much. Is the audio okay?
The audio is very good, yeah. So,
Okay. So yeah, let's talk about CTF and BTF debug support in the GNU toolchain. Yeah, so briefly, I want to first go. Sorry, I'll have to change the setup. I can't do it like this.
yeah, maybe don't listen to yourself. If someone wants to ask a question, then we'll raise the hand. How about that? So just speak to the microphone and don't listen to the earphones.
Yeah, I'll do that. So, yeah, let's talk about the CTF BTF debug formats now. So basically, in this talk today, first I want to briefly introduce the formats, and then give a brief update on what we have done over the last 1 year before I talk about implementation in GCC. And lastly, I want to spend some time today talking about our next phase for the project. So yeah, first things first, CTF and BTF debug formats are two distinct formats. They came into being to fulfill the need of conveying minimal basic type information. So CTF stands for compact C type format. It came into being in Solaris kernel and later was ported to Linux. The current version v3 is the v3 version of the Linux port. BTF stands for the BPF type format, and it also came into being for the same need, the need being to represent type information for the kernel. The current version is v1. Now, both these formats have the same common ancestor. So if you look at the header files and such, you'll see remarkable similarities. You'll see similar looking steps representing types and similar looking set of kinds. But the fact of the matter remains that these are binary incompatible and distinct formats. They are currently being maintained in two different groups and follow a very different evolution history, so to speak. So going into differences will not be possible for me today, but I thought I'll give a flavor of how the two formats look like currently and how they are evolving, just to drive home the point that the two formats do remain quite different from each other. So let's see the most recent addition that we have seen in CTF. In CTF, we've seen the CTF case slices being added in, I think it was 2019, yeah. So before this, CTF did not have a way to represent enum bit fields, and so now we do. On the BTF side, these most recent additions have been in the last few months of 2021. Going to further representation-related differences, CTF has support for multiple compilation units. So it has a concept called archives, which is used to arrange the CTF section. The CTF. So think of what the compiler generates as a CTF dictionary. So archives gives you a way to represent these dictionaries in a parent-child relationship. So you can. The linker uses this representation, the archive representation, after type deduplication, but archives may find a use case in other scenarios as well. And on the BTF side, there is no such representation. Probably it's not needed yet. And then on the library side, you have a libctf, and this libctf sits in the GNU Tools as of 2.36 onwards, and this is used by both the linker and the debugger. And on the BTF side, there is a BTF side, sorry, there is no libbtf, and there is no linker support needed yet either, it seems. But there is a libbtf which sits in the kernel, and it does BTF program loading and more. It has a wider responsibility than just dealing with BTF section, but understandably, it does let you open and inspect BTF section. So the needs are fulfilled. It's just that the library support sits a bit differently for the two formats. And the last one is probably the most representative of what I want to convey in this slide, which is that BTF is evolving very close to what BPF programs need. So if you look at one of these extensions in BDF, which is btf.ext, it's a new section, and it gives you information for CORE support in BPF programs. And so basically, it needs source location information and some weird-looking relocations, but all this to fulfill the needs of a specific use case of the BPF land, right? On CTF side, there is no such information that's needed to be represented. So CTF remains generic to this date, but BTF is BPF is very close to fulfilling the needs of BPF programs. Having said that, we have worked over the last 1 year to support BPF and CTF debug formats in the GNU tool chain. On the CTF side, now you have two command line options, -g GCTF and -g BTF, to generate the CTF and BTF sections respectively. On the GNU Tools side, for CTF, the support is also complete. The linker supports type deduplication, and you can use object dump and other utilities. On the debugger side, GDB can use the CTF sections and offer users some useful, debugging information if dwarf is not present. And the support for both single CU, single compilation unit, and archives exists in GDB. So by and large, it looks like, well, by and large, yeah, the support seems to be ready. So yeah, try it out with your applications and report issues if you see any on the channels that we know. On the spec side, Nick has done most of the heavy lifting here and uploaded as well all the documents on cdfstd.org. So this has been set up for not only sharing information, but also getting some feedback from all of you via the mailing list as well. Right. So yeah, I wanted to spend some time on the implementation aspects in GCC. We got some feedback in the past few iterations of the
Is it me or this is blocked?
No, looks like we lost Indu.
Oh, okay. Let's see.
We're going to give it a minute, see what happens. Do we have anyone else from the team who might be able to continue the presentation?
I could do I could try it, yeah. But it's better if she comes back.
Yeah.
I think Indu might be back. Indu, are you back with us?
I'm here. Sorry, I got disconnected. Am I still audible?
Yes.
Okay. So I'll keep my camera off in case it, helps the connection. I hope Yeah, so I'll start over from this slide. We have adapted the implementation after the feedback that we received from upstream that, yeah, do not use tree structures and do not use debug hooks because long-term, yeah, so basically, yeah. Hello? Yeah, seems I'm here. So
Yes.
at this time, yeah, so we haven't added any further debug hooks. What we rely on is the dwarf 2 debug hooks. What we have added is the gray block on the right side that you see. All that it does is it introduces new APIs, and those APIs are called from some of the existing debug hooks in dwarf 2 debug hooks. So the key takeaway from this slide that I wanted to say was that the dwarf generation remains unchanged. You can use -G and -G CDF together to generate dwarf and CDF or dwarf and BTF for any target. Well, for the targets that support those debug formats. And the second takeaway here is that, well, I can go over it in the next slide. So the gray block is what we will delve into in the next slide. Right. So the main APIs here of concern are the dwarf to early finish and dwarf to finish. And these are the two main APIs which are being used to generate CDF and BTF debug information. The APIs shown here in red are the ones that we have used in the debug hooks. And these are the APIs that we think are useful if you want to add a new debug format to GCC. So the dwarf to CDF utility is the one that takes the internal dwarf representation from GCC and converts it into an internal CDF representation. The APIs here, CDF add function, add array, and SOE, struct or union, are the ones that are used to update the CDF container. CDF container, think of CDF container as just is just the entity that defines what the internal CDF representation looks like, and it also holds the CDF types at runtime for you, right? And the emission is written in the cdfout.c and bdfout.c files, and at some point, yeah, you emit CDF and BTF. So the emission is placed here in early finish or CDF debug finish, depending on whether it's CDF or BTF debug format. CDF more for yeah, I would just say that CDF is always emitted early. For BTF, we do have a choice to make, and that's because of BTF core, CORE. But for this talk today, let's skip over that part for now. Yeah, having said that, so most of this infrastructure here is shared for BTF and CDF generation. So even for BTF, you would do the same flow. You would take the dies. So these are read-only dies for all of this gray engine. So you take in the dies and you create the internal representation in the CDF container. Now, because the two have a shared common ancestor, it is also possible to just, by and large, it has been possible to represent those, even the content necessary for BTF in the CDF container. The only difference that comes in for BTF generation is somewhere here, right? Before emission, you do some pre-processing, and also just after initialization, there is some pre-processing done. But yeah, that's it. That's all about the implementation in GCC. So far, using the dwarf dies has worked quite well. There have been issues, but yeah, we'll look at them as time goes. For GDP, GDP also uses libcdf to read CDF data and to present to user, type information and such. If dwarf is not present. Recently, the support for archives was added, so now it supports both single compilation and CDF archives. And the next steps for GDB would be to add support for CDF v4. Then we have that, more in a baked state, and also other format changes. Now, yeah, this brings me to talk about what we would like to get done next in this project. Yeah, we would like to continue to support CDF and BDF in the GNU tool chain. And the larger goal is to move towards CDF v4. So yeah, please hop on to cdfstd.org, and many of the issues will be open to talking and getting some feedback on the mailing list there. Before I get into CDF v4 specifically, there are a few slides that I want to discuss. This is something that I would like to spend time on. And so this goes in the direction of what is next for this project, right? One of the things that has come into light is this interaction of debug flags, the existing debug flags, and GCDF and GBDF. So essentially, in this specific case, it relates to the debug info level, but understandably, the issue, what I need to see is whether the dwarf dies, the set of dwarf dies that are generated, they are optimal enough for CDF and BDF generation. So one of the cases that has come out is debug info level. Basically, these two flags here, G level and G toggle, they update the debug info level, and so does GCDF, GBDF. So let's just look at the example to make it clear right away. G0, GCDF, G toggle. So the debug level hops from 0 to 2 to 0. Now, when the user, when she said G0, GCDF, G toggle, she probably meant give me some dwarf, but don't give me CDF. But what ends up happening is no dwarf, no CDF. So I think you get the idea. But yeah, so the solution here seems to be that we need to differentiate between how much of dwarf we internally generate versus what does the user want to be emitted, because now you have internal consumers of dwarf dies. Yeah, any feedback or any challenges that you see here on this problem would be appreciated. Next, this is another item that I noted when we were upstreaming the patches. In general, it did feel like if we modularize the dwarf to out functionality, it will be useful. One of the things that we were trying to get done then was just, we thought it would be useful to just add a dwarf to int.h, which is the interface that, say, for these debug formats, the interface that these debug formats might end up using. So base die type creation, and maybe some APIs for getting and setting attributes. But another suggestion that was made in this regard was, why don't you split off a dwarf to CFI.h? Now here, yeah, I need to probably get some feedback and also look further into it, research, and see which line of split makes sense and is doable, basically. And finally, yeah, there are some low-hanging fruits in preparing for v4. So adding some GCTF version command line options, and also making the container version aware. These are implementation specific next steps in GCC. And yeah, this seems abrupt, but let's talk about CTF v4. And so there are some areas where we would like the CTF format to be upgraded. Some of these are listed on the CTF STD website. We will make the information more clearly laid out over the next few weeks. But one of the items that has been sought after and also requested is the support for backtraces. So we would like to extend the CTF format to support backtraces with the following requirements. First, the backtraces should be available, should support asynchronous stack unbinding, and have support so that the original value of the arguments can be recovered. And do all this while keeping CTF principles in mind. So keep it simple and compact. So do not add complex expression encoding, no location lists, and no stack machine. And So one of the observations that has been made, none of this is fully baked, but it is, yeah, I would like, I'm discussing it first time um, publicly, right? So one of the observations here is around call site information. So each ABI defines parameter passing rules. So the first thing that it defines is, given a high level language type, what is the machine type? And the second thing that it defines is, given the machine type, how do you assign, or how do you do the argument marshalling? How do you assign the register and stack location and so on? So the thinking here is the debug format should be able to specify one and let the backtrace client deal with the number two. So in other words, what I mean to say is that it should be sufficient to just encode the natural location of the argument in some sort of a class. And the client, the backtrace client, should be able to figure out the exact location from the position, class of the argument, and the ABI. So if you look at, so AMD64 lays out these ABIs, these storage classes quite explicitly. Similarly, other ABIs, for example, AR64 lays out these in as the storage classes. So to make it perhaps more clearer, I have some examples on the left side, which is, say, for the first example, it's a function with 6 arguments. And in AMD64, you would see the arguments being passed in a specific order in the set of registers. Now, as far as the CDF, as far as the backtrace format goes, it should be sufficient to say that there are 6 arguments and each of storage class integer. The backtrace client should be able to then infer that these must be registers, and hence these are the locations that these are going to be passed in. Second example shows small aggregates. So as AMD64 says, anything less than 8 bytes is a small aggregate, and all of it will be passed via registers. So in this case, the 2 arguments are int a and struct parm s. The first argument is passed in RDI. The second argument has it's a small aggregate. So the first 2 members of the struct are passed in the same register, and s.d is passed in an XMM register. So as far as the backtrace format goes, it should be sufficient to just say this, that the first argument is passed in an integer, and the second argument uses 2 storage locations. Of those 2 storage locations, the first one is going to be integer, and for the second member, I'm not going to say anything because it needs to fall back on the previous one. It's the shared location, integer, and the third goes to an FP register. So the point that I think I'm trying to make is that if there is an unambiguous way to specify that information, then the backtrace client should be able to just do the marshalling easily. Last example is also along the same lines. So, but maybe we can skip it for now. Yeah, so basically we're trying to also go bottom up. What we're trying to do is just do the minimal necessary required changes for now. So let's define the CDF backtrace format phase 1. Phase 1 being get the original value of the argument from its natural location if it has not been clobbered. So the compiler gives you this information of whether or not it's clobbered, and gives you the storage location and in the backtrace format. And the client does the rest of the things. This may or may not be enough. This information may or may not be enough, but yeah, it would be good to see how many cases does it serve. So it's coming down to the following. We would need 2 CTF sections with relevant information. The .ctf section already exists. What we would need to do is add call site and call site parameter information. And the unwinding information will go into a .ctf frame section. It will need to contain 2 specific indexes. the call site index and the CFA index. Call site index being given a PC, I do want to go find out the call site record because that's where my storage classes and that information lives. The CFA index is the one that gives you the information about unwinding. Given a PC, what's the CFA? So yeah, linker will need to do the necessary work as well here. There will be some need to merge the CTF frame sections across multiple compilation units, and maybe some deduplication or garbage collection seems it might be necessary. The main the key takeaway here would be that we are still relying that the client may be able to do the part of the heavy lifting here by following some ABI specific methods of knowing the exact register and storage location. So with that, I would like to end and say that you can reach us on any of these channels, and I'm ready to take questions, if any.
Thank you, Indu. Anyone would like to ask some questions? We have 4 minutes.
Sorry about the connection troubles and the echo problem.
Questions? All right, well, thank you very much, Indu. Thanks for the status update. Looks like you guys are attacking some complicated problems. So anyways, thank you. Should we set up for the next presentation? We have 3 minutes before start. All right, let's take a small break and come back in 2 minutes. Mr. Jose, are you going to present today? Or is it going to be David or Guillermo?
Yes, but only for a couple of minutes. So
Only
be
for a couple of
happy.
minutes. I'm very sad.
Yes, well, yeah, me too. But that's how it is, you know?
Yeah.
So then at some point I will pass the baton to David Faust, who should be around here, and then Guillermo.
Sounds great.
So you do you take care of that?
Yep.
Cool. So should we start now?
Yep, you can go.
Okay, so yes, it's time again, you know, for a little update on the support in GCC and the GNU Tools in general of the weirdest compilation target ever conceived, at least in my opinion. Well, the summary, I will just make, you know, a very little summary of this because we don't have much time. Well, BPF, for in case anyone doesn't know what it is, BPF is a sort of a virtual architecture which is supported in the Linux kernel, and it originally was intended to be used for filtering packets, like network packets. Like when you get a network packet, you decide if you want to let that packet go or not. So for that, apparently, it is good to have a lot of flexibility. So basically, they designed, you know, like a sort of an instruction set of in a virtual machine in the kernel in which you can write your programs to decide, given a packet, to accept it or not. That was originally, then that evolved into a sort of a kitchen sink, you know, in the kernel, and more kernel subsystems are starting to use BPF, hooking BPF programs in many different places. Originally, only LLVM was able to compile C programs to BPF. So a couple of years ago, we decided to add support in the GNU Tools as well. So we introduced this port, BPF unknown none, which is now upstream and available for everyone who is lucky enough to work with BPF. So in this talk, basically, I will present now in 1 minute some general updates. Then David Faust will talk about the support for BTF, which is a debugging format associated with BPF, as Indu has already introduced in the previous talk. And the support for something called core, which means compile once, run everywhere. David will tell you in detail what it is and how painful was it to implement it. And also, well, some additional options in the compiler, like new command line options to support, you know, a sort of a version levels of the BPF instruction set. We will see that as well. And then finally, Guillermo will talk about the support for a few new instructions that the kernel chaps have added to the kernel to support atomic operations. So the port itself is completed. I mean, we have full GNU Tools support, you know, assembler, disassembler, also linker, even though the linker is not used, but it is supported. We have a full-fledged GCC backend that can compile C into BPF. We have GDB support as well. So GDB knows about the BPF virtual architecture, and you must be able to use GDB to debug your BPF programs. Associated to that, there is a BPF simulator, which is part of GCC, of GDB. So in theory, at least, you can actually run your BPF programs in the simulator and debug them like single stepping, you know, and breakpointing them with GDB. And well, we have also a board description in the GNU, you know, for the test suite. And some miscellaneous updates here, very fast. We added a couple of new instructions to something that we call XBPF or extended BPF. In particular, we added support for signed division and signed modulus instructions that BPF does not support, but we use them so So it makes it much easier for us to debug the GCC backend, basically. We changed the GCC BPF backend, so now it can emit DORF, debug info. We will see later that the main debug information for BPF is BTF, but nothing prevents us to generate DORF as well. The DORF that we are generating, that GCC generates for BPF, is not that terribly useful in some senses because this target is very, very particular, and there are things that we cannot express, right? In particular, call frame information and stuff like that. Anyway, but it's there. You can generate DORF for your BPF programs. We had to make several adjustments and fixes in the compiler to pacify the kernel verifier, because the BPF programs that you compile with, you make with the compiler, then you have to run them in the kernel. But in the kernel, there is something called the BPF verifier that looks into the BPF programs that you are uploading and decides if those programs are safe to be executed or not. Now, the verifier is very anal. I mean, it's a pain in the ass, basically. But okay, it has to be there. So it's not always easy to generate the right code for the program to be able to be running the kernel. Many bug fixes, and functionality-wise, and I am very happy that I can say this, finally, after a lot of work, we can tell that we are on par with LLVM in terms of functionality. So now there is no more excuses for anyone to use LLVM to build BPF programs for the kernel. I mean, you can do with a very small, slim BPF unknown non-GCC executable, which is at most 12 megabytes big, what you were doing before with like 8 or 9 or 10 gigabytes of LLVM runtime. Okay, so this was all I had to say about the general update about the project. So now I will let David to talk about BTF, core, and the new instruction level support. David?
Hello?
Yeah, there you go.
Okay, great, thanks. So the first thing I want to talk about is basically what we've already seen thanks to Indu, which is the BTF support that's now in GCC. This is just the BPF type format, and it conveys type information as well as general debug information for the kernel to load BPF programs and make use of. One thing that's interesting about the implementation in GCC is that it's supported for any target via the GBTF flag, and that means that, well, most of the time you wouldn't find much use for BTF information if you're not the BPF backend. You can actually do things like, say, generate BTF information for the kernel directly when you're compiling for x86 or AR64 or whatever your kernel is, rather than the traditional method, which has been to generate all the dwarf and then convert that into BTF for the BPF loader to use. Now, naturally, BPF is tailored to BPF programs, so if you want something similar but more general purpose, then that's what CTF is for, basically. So with that in mind, we can tackle some of the problems that BPF has had, which first of all is portability. And the issue here is that BPF programs are loaded into the kernel and they're going to interact with kernel data structures, which means in order to do something useful, they have to know definitions of those data structures. And this isn't limited to just user space APIs, but they can also be internal kernel headers. And the thing about those is they change a lot, even between subsequent versions of kernels. And that means that if the data structure definitions are changing all the time, and you compile your BPF program against headers in one kernel version, in general, you can't expect it to just work when you move it over to another kernel. And so traditionally, the solution to this has been to carry around a compiler between kernels and recompile your program from C into BPF on every particular version of kernel that you want to run on. But luckily, there is a solution, and it's already been implemented and designed courtesy of the kernel and LLVM hackers, and it exists already in the LLVM BPF backend. And that's this thing that Jose mentioned called BPF core, or compile once, run everywhere. This is basically just relocations for accesses to kernel data structures. And of course, in order to be able to have any information about those data structures, we needed the BTF debug with the type information. But now that that's available, we can finally implement this and give the kernel a way to know what instructions does it need to adjust at load time of the BPF program, and how to adjust them from whatever data structures the program knew about at compile time to those that are actually present on this kernel. And the way it works is pretty similar to most relocations that you would be familiar with. So say, for example, we have these two versions of the same structure definition, one for kernel A and one for kernel B, and kernel B has added a new field into the inner struct. Well, if we compile this program on kernel A, it only knows about this old definition. And if we go to load that into kernel B, it won't know what to do without core. So we generate this down here, this thing referred to as a core relocation. And this basically records the information that you would expect. It says, what instruction do I need to patch? What is the type information for the containing structure? Some form of an encoding of what field am I actually accessing in that struct, because if the fields have changed, something, the BPF loader in this case, wants to figure out how can I adjust these accesses to try to find the field that is the same field on this new version of the struct. And taking all this together, the BPF loader then has the information it needs to load a BPF program, take the BTF type information that's in there, process all of the core relocations, compare them against the BTF that is available for the kernel that it is loading the program on, and figure out how to patch the instructions accordingly. And once you do that for all the instructions that need relocation, now your program is suddenly portable from kernel A to kernel B without having to recompile it. And that is really nice for a lot of reasons. So all of that is now implemented in GCC. It's all contained into the BPF backend. So if you're any other backend, you don't have to worry about this strange form of relocations that aren't really relocations that are responsible, that are the BPF loader's responsibility to figure out. But of course, we needed the type information, and now that we have BTF, we can do that. But there is one thing here that I want to touch on a little bit, which is there's some unfortunate coupling with the .btf information. So the core relocations go in a new section called btf.ext, but this information here that records what field of the structure are we accessing is actually encoded into a string, and that string is stored in the regular .btf section string table. And this means that anytime we want to generate these relocations, we actually have to delay output of the debug until after we can generate all of those relocations, which turns out to be pretty late in the compilation process. And of course, the option that controls all of this stuff is this -m core option. By default, if you're generating BTF information for a BPF program, the core information will be done for you. You don't need to manually specify the option. It's implied because it's part of the debug information. So what the implementation actually provides is two things. First of all, there's a built-in, and this built-in is called preserve access index that's specific to the BPF backend. And the name here is chosen to be compatible with the same thing in LLVM. So the way it usually looks is something like this, where you'll have some information that you want to access, and you'll wrap the reference to that information in a call to the built-in. But it's a little bit weird because this built-in doesn't actually do anything. It doesn't change the semantics of the program. It's purely a transparent marker that tells the compiler, hey, I need to know information about this access here so that I can generate the core relocation information so that the program can be adjusted at load time by whatever kernel we're loading it on. And it accepts any type of expression, and it's just returns the result of the expression in here. And if you have many accesses to structs that you need to record this information for, you can do that with something like a statement expression, which you might have seen in the kernel if you're familiar with this stuff. But this gets pretty ugly pretty quickly. So there's a better way to do that, which is the attribute version. And this is basically the same thing as the built-in, but it says for any type that's attributed with this, and it applies to structs and unions, I care about every access to this. This whole struct might change between kernel versions, and I want you, the compiler, to automatically generate the relocation information for me so that I don't have to manually wrap every single access in a call to the built-in. And so this makes it a lot more convenient to work with. And that way we're able to generate all of the information that we need to support this compile once run everywhere mechanism that is the same that LLVM has. And it's a pretty cool thing because now you don't have to carry around compilers, you don't have to worry, and suddenly BPF programs are actually portable when you compile them on one machine and try to transfer them to another kernel. So that's basically it for core. Moving on to something pretty different, but also related, is specifying what features of BPF does the kernel that you're trying to run a program on actually support. And this is something that until now we haven't had a good way to specify in GCC. And that is, over time, as new things have been added to BPF, sometimes you could be in a case where you're generating code that is targeting a more recent version of BPF than the kernel that you're trying to load it onto actually implements. And these are things that have been added a long time ago. There was no support for compare and branch operations with a less than. It was only greater than or equal to. And over time, there have been support for new 32-bit ALU operations and 32-bit jump operations, which just are the same as the 64-bit versions, which are the default, but they treat the operands as 32 bits rather than 64. And most recently, the significant addition has been new atomic instructions that are supported in BPF, which Guillermo is going to talk about next. But now we have new options available, and these are just basically what you would expect, feature options that enable or disable, there's a negative version of those options to say, hey, my kernel has this or doesn't have this, so please don't generate code that would be incompatible. And this all sort of culminates in a MCPU specification that says, what sort of stable version of the BPF ISA am I targeting? And so the options here are basically the same ones that are sort of standard with the BPF hackers, which is a version 1, which is the very first one, version 2, which adds the additional compare and branch operations, version 3, which adds the 32-bit versions of ALU and jump instructions. And if you don't specify this at all, then we just default to the latest, which is currently a synonym for version 3. And this becomes convenient if you have some custom version of a kernel that you know implements almost everything that's in version 3, but maybe it doesn't have 32-bit jump operations for some reason. Then you can combine them and just disable those operations. And with that, I will hand it off to Guillermo so we can learn about the BPF atomics. Guillermo?
Meanwhile, while Guillermo comes up, Tony had a question. I propose we wait until the end to have questions depending on time that we have left. But maybe if you could just stick around, David, after the presentation.
I can't get the chat to load, so if someone could relay that question, I don't know.
Yeah, I think the chat is malfunctioning because they're creating accounts. That's what I read. So I will do it by video, and if we can, then we'll use one of the hack rooms.
Okay, perfect. Thank you. Guillermo, take it away.
Okay, thank you, Dave. Okay. Okay, we will talk about the implementation for the atomics instruction in the GNU Tools chains. And as we know, the BPF program was designed to be executed in a kernel space, and the kernel code is executed in the asynchronous way, in some cases in preemptive behavior, in other many cases as a parallel execution. And of course, the BPF program are no exception. The same code can be executed on behalf of two different processes, or more than one thread can be executed the BPF code with the same data in the same process. Therefore, the data could be shared with other part of the system, and concurrency problems can be arise. Then the BPF developers have found themselves need to implement manage some strategies to handle the concurrency issues. So synchronization mechanisms are implemented in the BPF code. One of them is the spin locks. The spin lock helps to protect data that is handled in a block of statement of the code by using the kernel function BPF spin lock and BPF spin unlock. It promotes the reentrancy pattern to gain fine granularity to handle such critical section. But another Second alternative that we have to manage such concurrency issues is the atomic instructions. Instead of protect data in a block of code that is focusing to synchronize the access in a single piece of data in the critical section. The support in the kernel was introduced at late 2020, along with the documentation describing the fields, bits, instruction, and much more used to encode in the code such kind of instructions. So the instructions supported by the kernel and described in such documentation are add, and, or, exclusive, or, exchange, and compare and exchange. Worth mention here that one comment was written by designer and maintainer of atomic instruction in the Linux kernel. That mentioned that they are using the immediate field of the instruction to extend the opcode for the atomics instruction. And it is showing the following picture. As you can see, and the design of the new instruction, they are using the operand field of the instruction as an opcode field. This introduced some complication because the content of an operand field is indexed dependent. As you can see here in this picture, the bit 32 to 39 is the immediate field, but now the opcode is split in two different bytes, shown in the screen squares. Our porting is based on the CGN framework that is used in GNU Tools to generate the opcode structure for a particular target, trying to guarantee that the CGN is able to generate the right structure for the new eBPF atomic encoding. A couple of limitations in that framework was found. The first one is that it wasn't able to provide the support to compute the mask for getting the correct values for constant fields. These constant fields are used for the atomic source opcodes. And the second issue found is that we already fixed to correct the calculation in the mask and value when the field is defined in a long form instead on a short form, and the offset is different to 0. Next, after add the CGN support, now we were able to describe in a natural way the atomic instruction in the CPU description file for the eBPF target. So basically, we add DNA of the five normal instruction listed in the documentation in the machine description file for the eBPF target. And also the definition, some definition were added to be run on the simulator. But since the architecture in the BNU, since some other architecture relies on the GNU Tools, and the CGN framework, the previous patch is modifying some core stuff. So carefully an internal revision was done, and a complete regression test was required to guarantee that no side effects were introduced for this architecture, for the eBPF architecture, in the other ones. This table shows that the syntax that is used by new assembler for atomics encoding. As I already mentioned, there are two different encoding for atomics of code shown in the last column, because the opcode value is indexed dependent. Okay. And finally, this is an example of the disassembly atomics instruction using the Linux tool chain. We have adding support also for the GCC for atomics building functions. This implementation is fully compliant with the GCC building function provided by those buildings that generates the atomic instructions. To bring the GCC support, basically we add some definitions for the atomic instruction in the BPF MD file that is the backend for the eBPF targets, as I show in this example. For instance, adding the support for the add atomic instruction, eBPF add atomic instructions. since the atomic instructions are using implicit destination and operands registers, that in eBPF always is the R0, a new constraint was added in the backend to make sure that the register is used for the BPF instructions. In that case, this example shows the compare and exchange atomic instruction for the eBPF target. And finally, we have an example running point to point from the C source code to get the object file to be installed or loaded by the kernel verifier and run the eBPF program. And that's it.
Thank you, Guillermo. Thank you, Jose and David as well. So if I remember correctly, it was Tony who had a question?
Hey, sorry, hunting for the button. Yeah, I was curious as to how the references are done for the relocations. I mean, how it looked like an example you had. It was some numbers. So if it's like the 5th declaration, then what happens if there's been declarations put above it? And then obviously the question, well, what if the semantics have changed? How's that kind of captured?
For the core relocations, right?
Yeah, exactly. Yeah.
So in BPF, the way that instructions are referred to in both the loader and the verifier and things like that is they're always referred to by an offset from the beginning of the section. So that way you know what instruction you're looking at. And for the declarations, when you're compiling the program, you have to know exactly what that type is that you're referring to, right? So you have a definition of the struct, and you have all the type information for it that's in the BTF section. So to refer to a particular field in that struct, there's the string encoding, which was shown briefly, but basically that's a zero-based index for the position of the field that you're accessing in that struct. And it nests. So the colons that are in that syntax separate layers of the field. So maybe we could go back to that slide actually and see.
But I mean, is the first number which declaration? I mean, what if if it's maybe it was the 5th one and now in the new kernel it's the 10th one? Does that mean you're now
right?
One?
So the key is that the BPF loader at load time, it has type information for both the program that you're loading and the kernel that you're loading it onto. And so it uses that core relocation to figure out as much as it can about the fields in the struct that the program accesses. And then it has some way internally to figure out how to match those up to the kernel versions. And it's possible that it doesn't have enough information to do so and will fail.
So it's trying to like do name, like here's a name that's roughly the same.
So because
maybe you added a V3 on the end, but it must probably mean the same as that V2 one over there kind of thing.
Right, exactly. So because the indexes are encoded in the string accessor, it can look up all of the detail about the struct members in the type information. Because the BTF information has stuff like what is the member called, what is its base type, all the things like that. And so it can match them up.
And then dealing with semantic changes, that's just, buyer beware. I had a field and it meant this.
Yeah, sure.
The same name field that has different semantics and you're just out. Okay.
It's not a perfect solution, but it's better than not having one.
Yeah, thanks.
Any other questions?
I guess maybe I could have another one. I mean, what's your assessment? I mean, as far as I can tell, BPF is really giving a lot that Dwarf does. So how does one compare and contrast these two ways of thinking about things? I mean, is one better than the other? Are they serving different needs? Or, in some future world, could there be a unification of it or etc.?
Yeah, that's not entirely clear to me either, to be honest. But the key, I think, is that the BTF information and all of the extended stuff like the core relocations and everything are very much designed by the needs of the kernel. And so everything that goes into them is from a kernel perspective. What's the information that we need? What would be useful to have? And how do we pack that into a debug format that can be added into these programs? And I think the key problem with Dwarf is probably just that it would be too big and complicated for the kernel to want to figure out at the time where it's loading a program. But maybe Jose can add more.
Well, I mean, Dwarf in comparison, BTF is compact. It's much like CTF. Actually, they share the same ancestor, right? And when it comes that you are interested in, I don't know, information about some C types, how big is the Dwarf information for a complete build kernel nowadays? I don't know, gigabytes? Maybe huge, right? And right now, the kernel people, what they do is that they build the kernel, they generate the Dwarf for the kernel, and then there is a component in the kernel, of which I think the maintainer is here in this talk, actually, I think, translates the Dwarf of the kernel into the BTF for the kernel. And I think that the translation is just a megabytes big, right? For the BTF information for the complete kernel.
But presumably Dwarf doesn't want to deliberately be big. So, I mean, if BTF has solved the problem of making it smaller, then why wouldn't Dwarf want that benefit too?
Yeah, right. This is not a criticism against Dwarf. This is
well, I guess my bigger question really was just, there seem to be these two ways of thinking about doing this. I'm just trying to comprehend, is there something that is the best of both, or is one just point blank better than, more capable than the other? I mean, if you look at the Infinity project, I mean, they were moving towards, trying to have a way of describing more of this stuff. And I think one of the folks working on it was looking at BTF as a way of kind of achieving that. And, rather than using it just seems like the goals are very similar to me.
Yeah, but that's one of the reasons why we took that much pain in introducing support for CTF and BTF in GCC. And not just for the BPF target, for every target. I mean, there are domains, there are applications where Dwarf is either too complicated to interpret, or too inconvenient, or too big, right? So for those situations, a simpler format may be better.
So do you see things that Dwarf does that BTF can't do, and that's why it still makes sense to, be thinking of it?
Things that Dwarf does and BTF doesn't.
I think the other way around. Yeah. You were mentioning, Jose, at the beginning of the presentation that for BPF, you're capable of generating Dwarf debugging information. And then you said that it's actually not very useful because Dwarf wasn't really well tailored for what BPF needed to do. So maybe that's a clue.
No. Those limitations come from the fact that the BPF architecture is very peculiar. Mm-hmm. And so, for example, the stack is disjoint. So, and this all comes from security aspects in the kernel. Like, for example, when you call to a subprogram in BPF, you can pass a pointer, an absolute pointer that points to some location of the stack of the caller to the callee, and that's legal. You can refer to that pointer in the callee, but you cannot actually access the stack frame of the caller using a relative offset to, using the stack frame as a negative, or sorry, a positive, that would be a positive, right? A positive offset, right? Because the stack is disjoint. And if you try to do something like that, the verifier will complain and not load your program. So with that kind of limitations, it's so difficult to generate call frame information in Dwarf, right? For BPF programs, for example, because it's complicated. So that's what I meant. But the limitations, they don't come from the fact that DORF is limited or anything. It comes from the fact that the BPF virtual architecture is very, very restrictive.
We're about 5 minutes over time, so we could continue those discussions in a hack room if you guys are interested, or if all the questions have been answered, we could stop here.
Yeah, I mean, I'm very interested to learn more. If anybody were interested, it'd be cool.
Well, and for CTF, which is very similar to BTF, also in domain, maybe you will find it interesting to join the discussions in the CTF std.org mailing list.
Okay, thanks, Josie.
We need DORF experts there.
I don't know that that's me, but I just yeah. No, I'm just trying to just comprehend how these two things kind of relate to each other. Yeah. I mean, it just seems like some of the things that you kind of tackling there seem things like, as I kind of look forward in Dwarf, just seems like they're similar things. And if there already are solutions, then, yay, kind of thing.
Well, all I can say is that while I don't, keep in mind that here, with the support in the toolchain of BPF and associated technologies, the technologies we are implemented are basically given, right? I mean, the main use of BPF is the kernel, obviously, and it makes full sense that it is the kernel hackers who are evolving, right? The technology, the instruction set, how it works, right, and so on. But in this particular point, I totally agree with them that probably DORF is not the best. I mean, something like BTF or even CTF and it works. I mean, this core mechanism is very impressive. The fact that it actually works, it works, and it works well. So.
Oh yeah, I mean, I definitely see that. Hence, if there's goodness there, then spread it around, kind of thing. I don't know. Did you want to go to a hack room and just talk?
Yeah,
a bit
sure.
more?
Which one?
Let's say hack room. Well, anyone you want. Let's just say number 1, since they're all free.
Okay, let's hope that some kernel hackers will join there too, because they are probably in a better position than us to talk about, BTF, and core and so on.
Remember, sorry, Elena here. Remember, there is the toolchain micro conference as well on Friday, where we can discuss with the kernel people. And remember, there is a keynote starting in 10 minutes as well.
It's true.
Yeah,
okay, well.
But you can go to the hack room if you want.
Hack room number 1. Okay, see you there.
All right.
Ciao.
Thanks
you all.
And see you guys tomorrow. Bye.